Hello, Kirjan sir.
Yeah. Tell me.
Can we start now?
Yeah, we can start. It's almost 120, 118 people are there.
Yeah.
We can start now. And others, let them join slowly, no problem.
Yes.
Otherwise, we'll be losing a lot of time.
Wait. A very good morning to all. Welcome to second day session of the workshop. Today's session will be on FTIR spectroscopy. And I'm very happy to inform you that we have got excellent feedback regarding yesterday's session. As requested by the participants, we'll be sharing the recorded sessions links with the participants to their emails very soon. And before we start today's session, I would like to introduce an important person. He is Mr. Kanampalli Rajshekhar, Senior Territory Manager in Toshwin Analytical Private Limited, who is instrumental for conducting this workshop. When I approached him regarding workshop, he directed me to Mr. Girjan sir, which happened to be the best choice. And I am very thankful to you, sir. Now I request Mr. Rajshekhar to speak few words with the participants and also should tell about Toshwin Analytical Instruments Private Limited. Over to you, sir.
First of all, thanks for the opportunity given to us to present our instrumentation range to your university. And Geetham University is very well known to me. When I was even working in Hyderabad in same company, Toshwin, I used to visit Vizag branch and Hyderabad, and after coming here, Bangalore. So I am associated with Geetham. I would like to present few slides regarding Toshwin, our company, and our strengths, and what are the instruments we are dealing. Those details I want to present for 5 minutes, madam. I would like to take, yeah.
Sure, definitely.
Hello. Hello.
Yes, Rajshekhar, we can hear you.
You can able to see the screen, sir?
Yes, Rajshekhar.
Yes, sir, it is visible and very clear. Please go ahead.
Toshwin Analytical Private Limited is started in the name of Toshniwal Group in 1948, madam. We have got overall 72 years of experience in the analytical instrumentation, supply, services and all. So we have got a network of 14 branches and 24 service sites all over India. Most of the state capitals, we have got our sales and service units, and we have got remote service centers also. We have got total strength of 324 people And sales and support, service support, we have got almost 300 people. Other people are support staff. And further to this, I would like to mention what are the principles we are dealing with. You know that Shimadzu we are dealing since long time. This is the 50th year we are associated with Shimadzu. And apart from Shimadzu, we also deal with pre-chem instruments for microwave digestion systems. They are from Shanghai. And Oxford Instruments for benchtop NMR. This is a benchtop NMR which is it doesn't require any uh, liquid nitrogen. Cryogenic is not required. You can use just like as a FTIR in the instrument in the laboratory. And next we have got some consumables like Restec for chromatography products and SPECAC for FTIR accessories. And MEMMERT we are dealing for laboratory ovens, incubators, and sterilizers. So this MEMMERT we are dealing in some of the part of the India only, not entire India, madam.
Okay.
And apart from that, uh, we have got overall more than 15,000 instrument installation base in India for Shimadzu products. And in that UV more than 8,500, GC more than 3,000, FTIR more than almost 2,000, GCMS and MSMS instruments, almost 600 instruments are there, and elemental systems, ICP, AAS and ICP-MS more than 500 are there, and other instruments more than 500 we have installation base. And this is our key achievements. And our major customers are from pharmaceutical, chemical, and majorly academic and research institutes and universities, and testing labs, food and flavor fragrance companies, and petroleum companies. So these all are the companies we are covering, madam. We are supplying everywhere in the India, all customers. And these are a few of our customer base. So you take any name in the industry, we are present. Any pharma, chemical, research institute, Shimadzu is present in India. And these are a few valuable customers. And this is the range of promotions we are doing with all the uh, exhibitions and all we are promoting in the India. So this is the some of the stalls we have participated. And this is we have got even training center in Mumbai, SAAP, Shimadzu application laboratory also is present in India. Along with in Delhi and Mumbai, we have got laboratories where we can give the training for the students or customers, which is free of cost, but we have to register priorly to come there. So each and every instrument we are presenting is available in Mumbai, and we can give the trainings also. And, yeah, this is our corporate presentation. Along with me, my colleague Mr. Suresh also is present here.
Okay.
Suresh, would like to add anything?
No, Rashika. Good morning to everyone. Good morning, madam. Thanks for giving this opportunity.
Yeah.
And it was a pleasure working with Geetham University. So I think Mr. Girijan will take over now onwards. Girijan sir.
Okay.
Yeah,
Thank you,
over to you.
Suresh. Thank you. Good morning.
Yeah. Before that, I request our colleague Dr. Vikram Baswa to brief about today's program and introduction about FTIR spectroscopy.
Rajshekar, you can stop sharing your screen.
Yeah.
Thank you very much, Dr. Sri Lakshmi. That was a wonderful presentation about your company, Mr. Rajshekar. I'll soon be approaching you for a quotation on one of the instruments which you were talking about. Hi everyone, morning all the participants, morning Mr. Girijan. Thanks a lot for the wonderful presentation yesterday about ultraviolet invisible spectroscopy, where we talked about the construction working of a UV spectrophotometer. And apart from that, you talked about the derivative spectroscopy and multi-component analysis and a lot of other points about, important points about the UV visible spectroscopy. And everyone, Mr. Girijan will be talking about FTIR, the Fourier transform infrared spectroscopy. Infrared spectroscopy or vibrational spectroscopy is an analytical technique that takes advantage of the vibrational transitions of a molecule. It is used to measure the vibrations of atoms between the atoms, and based on this, it is possible to determine what kind of a functional groups the molecules have, whether they have an aldehyde or a ketone or an ester or an alcohol. So basing on that, you can determine, basing on the FTIR analysis, you can determine what kind of functional group is present in the molecule that you're analyzing. And the method or technique of infrared spectroscopy is conducted using an instrument called as the infrared spectrometer, or also called as a spectrophotometer. And that's what you'll be getting an infrared spectrum from, and that's going to be helping you to analyze what kind of molecules you're analyzing. And it would be great, Mr. Girijan, if you can add a few points about drift analysis, which is diffuse reflectance infrared for your transform spectroscopy as well in your presentation, because I mean, if you can add a few points on that, that would be wonderful, because it's not something which is regular FTIR, it's a diffuse reflectance which is used for powder samples. And I think that's going to be a valuable information for all the participants in this session if they want to analyze compounds which are not soluble in any solvent. Thank you. Mr. Girijan, the screen is all yours.
Thank you, Dr. Vikram. And as per your request, I'll be talking about diffuse reflectance measurement also. That is going to be a part of my program today.
Thank you.
Okay. So, good morning, all the participants and all the students. And before I start with my presentation, we have a small exercise to complete. I mean, within a period of not more than 2 minutes. Yesterday, my last slide was 5 questions on UV, and I hope the very, very simple questions I have given you. And I am going to ask these questions. Anybody can unmute your microphone and answer. I'll be happy. Number 1, what is the requirement of a sample to be analyzed by ultraviolet spectroscopy equipment? By a UV spectrophotometer. If you want to analyze a compound by UV spectrophotometer, what is the requirement? That was the first question. Anybody can answer, not an issue.
Someone raised his hand. Sunanda Thakur. Would you like to answer the question? Sunanda Thakur.
We have only limited time, 2 to 3 minutes maximum, because I have to cover a lot of things. Otherwise, you'll have to sit late. I have no problem because I am used to this. I have no problem.
Sir, yeah, please answer that question, because
okay, for any sample to be analyzed by UV, the minimum requirement is the compound has to contain a chromophore. As simple as that. The compound has to contain at least 1 chromophore, then the sample can be analyzed by UV, otherwise not possible. Very simple answer. I think most of them must be knowing. I think they are a little reluctant to come out with an answer, I suppose. Okay, I will go to second. It's very clear to all the students, I suppose, because that was the point which I started with yesterday morning.
Actually, one of the participants, Manu Trivedi, he answered in the chat box. It is a chromophore.
Oh, very good. Excellent.
Yeah,
right
yes.
answer. Okay.
Yeah, very good.
The second one. What is the overlapping region in the scant range? And what exactly happens here in this range? In this region. I am repeating the question. What is the overlapping region in the scant range? And what happens here? That is the second question. Any answer coming forward?
If you can't speak, you can just post your answer in the chat box.
I'll be happy if someone can openly speak. I'll be too happy.
Yeah, we will allow them to speak, but since
and even if you make a mistake, there's not a problem. We are here to correct you. So, but
yeah.
What is more important is you have to open up your mouth and speak. That is more important.
I don't think the participants can talk.
Okay.
Because it's only for the panelists who can talk.
Yeah. So for the benefit of the students, I only will answer this question. The overlapping region in the spectral range is between 360 nanometer and 400 nanometer. And in this region, lamp changeover takes place, either from UV to visible or visible to, because you know there are two lamps, one is a deuterium lamp and one is a tungsten halogen lamp. The lamp changeover takes place in this region between 360 and 400 nanometer, and that is why precisely it is called a overlapping region. That's answer. So I'll go to the next one. What type of a transition is taking place in UV visible spectroscopy? And that was what we started with yesterday when we started about the UV. What type of a transition is taking place in UV spectroscopy? I think I know every student will be knowing this. Everyone will be knowing this. But anybody can answer this. Anybody can answer.
Participants, if you want to answer, raise your hand so that I will allow you to talk. Otherwise, yes, sir. One answer came. Dr. N. Kanagatara.
Okay.
She told electronic transition.
Absolutely right. Absolutely right.
So many answers are coming up. Electronic transition. Yes, great.
Electronic transition. That is
Yes,
a very basic thing about UV. I'm so happy so many people have answered the question. Okay, yes. Now I'll go to the next one. What is meant by linear range of measurement and what is its importance? Yesterday there was a slide also on that. And if you had seen the slide, you will be able to answer this without any problem. What is meant by linear range of measurement and what is its importance?
Please raise your hand or otherwise post your answer in the chat box.
Any answer in the chat box at least?
Not yet, sir.
Okay.
They may be thinking.
Okay. So anyway, I will only answer because time is very precious for us now.
It is saying that one answer, sir, from Anusuya, relation between concentration and absorbance.
Okay, to a certain extent, that is a correct answer. Yeah. See, when you are increasing the concentration, your absorbance also will increase linearly to a certain extent. When I am increasing my concentration, proportionately, there will be an increase in absorbance, but only to a certain extent. Beyond that, even if I am going to increase the concentration, absorbance value will not increase. So it is the range where there is a linear relation between the absorbance value and the concentration is called the linear range. And the importance is when you are making a measurement, if your absorbance value lies outside this range, your quantitation will not be correct. So whenever you are making a measurement, your absorbance value should lie within this linear range. And that is what is known as linear dynamic range, LDR, linear dynamic range. And that is why we are always specifying, please dilute the sample to get a absorbance in this linear range. Otherwise, your quantitation will not be correct. That's the answer. And then go to the last one. If a sample has a very low concentration and the absorbance value is also
very to interrupt you, sir. The linear range should be 0 to 1, right? Intensity. But 0 to 1 is the intensity should be in between 0 to 1. That should be
normally speaking. Actual in most of the cases, the absorbance value should lie between 0.3 to 0.1, 0.8. That is why we always give a y-axis range of 0 to 1 absorbance.
Yeah, that is what is called linear range. Beyond beyond 1, it goes to non-linear.
Non-linear range. Non-linear.
There is no agreement between concentration and absorbance.
Correct.
They are not directly proportional anymore beyond 1 intensity.
Absolutely right.
So 0 to 1 is called the linear range.
Linear, yeah.
Yes. Thank you, sir. So next
the last question is, if a sample has a very low concentration and its absorbance is very, very low, how will you increase the absorbance of the sample for proper quantitative analysis?
We got one answer, sir, from Manu Divedi, by adding oxochrome.
No, that is normally if the sample quantity is very low, sample has very low concentration, and I am actually referring to an accessory that can be used to increase the concentration. If the students remember the one of the last slide which I have shown them yesterday, long path length cell, because it is directly related to Lambert's law. Concentration absorbance is directly proportional to path length, that is Lambert's law. So if my concentration of the sample is very low, sample quantity is very low, I cannot increase the concentration. I can increase the path length. Instead of using a standard 1 centimeter cell, that is 10 mm cell, I can go for a long path length cell like 20 mm, 50 mm, 70 mm, like that. I can increase my path length. And because the path length is increasing, my absorbance is going to increase, because A is equal to epsilon multiplied by L multiplied by C. L is the path length. So if the L is going to increase, A is going to increase, because there is a direct relation between absorbance and path length as per Lambert's law. So that is why we are giving long path length cells for these type of samples. Because every sample you cannot convert by chemical derivatization. Like yesterday I told you, sir, but that is not applicable to all samples. But a long path length cell is applicable to every sample whose concentration is very low. That is why we are offering different path length cells. Long path length cells are available, up to 10 centimeter path length cells are available for these type of samples. Okay, I think these are the very 5 basic questions. And today also, end of the program, I have prepared. I'll be giving 5 more questions on FTR also. So now I think let us start with the topic.
Just curious, sir, Girijan sir.
Yeah.
So with the 10 cm path length cell, what is the sample volume it should take?
Sample volume will be few ml. Exactly,
few ml
it will be few ml. Yes.
Few ml.
Yeah,
because normally with 1 cm, it will take 1 ml, 1 to 1.5 ml. 10 cm means it will be taking more sample only.
Yeah, sample volume will be more, but only concentration, but volume is more. Volume will be more.
Okay.
Yes.
Okay, thank you, sir. Please.
Okay, so
go ahead and start today's session.
I'll share my screen now.
Yeah.
The screen is audible. Sorry, the screen is visible.
Yes, sir.
Okay. So once again, good morning to all. Welcome to the second day of this webinar series. And today we have a very interesting topic, infrared spectroscopy, which is an excellent identification technique for different types of samples. So when we talk about UV, we know it is an excellent technique for quantitative analysis. It has got a lot of limitations when it comes to qualitative identification. But in the case of IR is a predominantly qualitative identification technique, even though IR also can be used for quantification. But IR quantification is a little difficult as compared to UV. I will tell you the reason, okay, later. So today, 95% or more than 95% of the users are using infrared as a qualitative identification technique. And we are going to see a little bit about the basics of IR, some of the important accessories, and some of the major applications. Okay. Now, when you talk about IR, whatever I know every student will know IR is normally used for identification of functional groups. So there is there are some people even who call IR as a functional group spectroscopy, because by carrying out an IR analysis, you will be able to understand what are the possible functional groups in a sample. And once you know the functional groups, you know what type of a class of compound it is, whether it is a ketone, whether it's an aldehyde, whether it's an alcohol, whether it's an amide. I mean, that sort of a classification you will come to know from once you are able to identify the functional groups present in the sample. So IR is a very valuable technique, especially when it comes to identification of compounds. And this technique is widely used in various segments like pharmaceutical industry, chemical industry. You name an industry, we have got a lot of applications there. Polymer industry, lot of applications are there. So let us see some few basics about this. I know, as I told you yesterday, we are only trying to refresh what the students have already learned and what they already know. Okay, and we are not going to teach you something new. These have all we have already learned in your classroom, but we are trying to refresh it. Okay. So IR is a member of electromagnetic spectrum. We have yesterday we had seen that electromagnetic spectrum. So IR is also a member in that, and IR is a heat radiation. Infrared is a heat radiation. It is a non-destructive radiation, whereas UV radiation is destructive. IR is not. IR is a non-destructive radiation. It is a member in the electromagnetic spectrum, and it has got a total wavelength range starting from 0.76, means approximately 0.8 micrometer, and it can go to 1 millimeter. 1 millimeter is 1000 micrometers. So you can imagine the wavelength range of IR is much larger as compared to UV. UV has got a shorter wavelength range, whereas IR has got a much wider wavelength range starting from approximately 0.8 micrometer, and it can go to 1 millimeter. 1 millimeter is 1000 micrometer. Okay. So this yesterday, of course, you had seen. So it's electromagnetic spectrum, and IR is a member in this. And the total IR region, what we are talking about, some 0.8 micrometer to 1000 micrometer, it is going to be divided into three different segments, three different parts. The first part is called near infrared, or it is simply called NIR. And the middle part is called only IR, or some people call it as MIR, mid-IR. And the last one is called far IR or FIR. And every segment has got its own applications. FIR has got its own applications, NIR has got its own applications. But the most important part of the spectrum is the middle part, MIR, or it is simply called IR. And that is a part which is more informative for a pharmaceutical chemist, an analytical chemist, an organic chemist. I mean, so that's the most important part of the spectrum. And most of the time, when we are recording the spectrum of a compound, we will be recording the spectrum only in the middle portion of the IR region. Okay, so what are the infrared spectral range? See, right from 14,000 inverse centimeter to 4,000 inverse centimeter, that's a region covered by NIR, near infrared. 14,000 inverse centimeter to 4,000 inverse centimeter. If you go below 14,000, you are going to higher energy side, you will go to UV, and beyond UV, you will go to X-rays, and then cosmic rays and gamma rays, and all very high energy radiations. So 14,000 to 4,000 is the NIR region, and from 4,000 to 400 inverse centimeter is the mid-IR region, and that is the region where we are maximum interested, 4,000 to 400. So every infrared spectrophotometer, when you are recording the spectrum of a sample, you'll be recording the spectrum from 4,000 to 400 inverse centimeter. That is the mid-IR region. And then from 400 inverse centimeter to 4 inverse centimeter, we have got FIR region, that is far IR region. And if you go below 4 centimeter inverse, We have got other waves like microwaves and radio waves, which have got extremely low energy content and very, very high, very long wavelength region. So on the extreme left-hand side, you have high wave number, higher frequency, very high energy, and shorter wavelength. And extreme right-hand side, you have very lower wave number, lower frequency, very low energy, and longer wavelength. So our IR is coming in between 14,000 to 4 inverse centimeter, which is divided into NIR, MIR, and FAR. So we are going to discuss only about the mid-IR portion from 4,000 to 400 inverse centimeter, which is by the most important segment of IR spectrum. Now this, of course, yesterday we saw this. When a radiation is propagating through a medium in the form of a transverse wave, it has got certain properties like transmission properties, absorption, refraction, and reflection properties. I mean, we had seen this slide yesterday. And what type of a transition takes place when a sample is subjected to a certain type of radiation? If it is a high energy radiation like UV, that was our yesterday's discussion, electronic transition. But when we talk about a low energy radiation like IR radiation, we are going to discuss about vibrational transitions. And there is one more, rotational transition, which is normally studied by microwave spectroscopy. It can also be studied by Raman. So when we talk about infrared, we are only going to concentrate on vibrational transitions. What type of vibrational transitions are going to take place in a molecule when it is exposed to IR radiation? This is all our study. This is all our basic about IR. And what is vibration? When I say vibrational transition, what is vibrating in the molecule? Everyone knows molecules are made up of atoms, and there are different types of bonds in a molecule, and these bonds are continuously vibrating even under normal conditions. So a chemical bond under normal condition is always vibrating with a certain frequency, which is known as the fundamental vibrational frequency of the bond. And this vibrational frequency can be different depending upon the type of the chemical bond we are talking about. Okay, but for every chemical bond, there is a fundamental vibrational frequency even at normal conditions. Okay, now these vibrations are going to change when it is subjected to a low energy radiation like infrared radiation. Okay, to understand this, what type of vibrations are going to take place, for is we are going to take a very simple group, a methylene group, CH2 group. Very simple group, CH2, one carbon and two hydrogens are attached. So there are two carbon hydrogen bonds in a methylene group. Forget about the other two. You only concentrate on methylene group, CH2 group. And then with the help of this methylene group, we are going to see how many types of vibrations are possible in a molecule. First of all, let us understand the vibrations are going to be broadly divided into two types. One is stretching vibration and one is bending vibration. Let us see what is stretching vibration. Stretching, from the word itself, you understand what is happening. Stretching. Suppose if you have a very flexible rubber tube, you hold it with both your hands and try to pull it from both the ends. Using your hands from both the sides, you try to pull this rubber tube, and it is a very flexible rubber tube. What will happen? It will elongate. When it is elongating, the length of the tube is going to increase because it is a rubbery material. It's a flexible material, and when you are pulling it, it is going to stretch, and the length is going to increase. Okay, so there is a increase in length when you are trying to stretch it. And now you leave your hands, what will happen? It will come back to the original position. Okay, so this is one possibility. Now again, you take this flexible tube and keep it between both your palms and then try to press it from both sides. What will happen? It will get compressed. So when you are pulling, it is elongating, and when you are pressing it, it is actually compressing. And when it is compressing, the length is getting reduced. There is a reduction in the length. So Either the length is decreasing now. But whatever is happening, so there are only two possibilities. Either the length of the tube can increase or the length of the tube can decrease. Only two possibilities. Okay. But whatever is the case, whether it is increasing or decreasing, if you are putting a normal perpendicular, if you are drawing a perpendicular on this tube, during the stretching process and during the compression process, there is always a 90-degree angle. That is, the angle is not changing. If you are drawing a perpendicular on this tube, during the stretching process and during the compression process, the 90-degree angle is not going to change. It will remain 90-degree only. And what is happening? Only the length is increasing or decreasing. And this is what is happening when you talk about a stretching vibration in the case of a molecule. So remember, now let us look at the first CS2 group on the left-hand side, top left-hand side. Center one is the carbon and two hydrogens are attached. The blue colored are hydrogens attached to carbon. So there are two carbon-hydrogen bonds. And during the stretching vibration, either the carbon-hydrogen bond lengths can increase or decrease. But the bond length is going to remain exactly same in the case of stretching vibration. Now, this stretching vibration is divided into two types. One is symmetric and another one is anti-symmetric. What is the difference between these two? You can immediately make out looking at the slide. So first one, let us look at the symmetric stretching. In the case of symmetric stretching, both the hydrogen atoms are moving in the same direction. Either they are going away from the carbon simultaneously or they are coming towards the carbon simultaneously. That means either the bond lengths are increasing simultaneously or the bond lengths are decreasing simultaneously. That is why the arrows are in the same direction. You can see that. And that is why, so they are either increasing or decreasing simultaneously. We call it as a symmetric stretching motion. And what about anti-symmetric? Anti-symmetric, you see now the arrows are in the opposite direction. When one bond length is increasing, another bond length is decreasing. That means when one hydrogen is trying to move away from carbon, another hydrogen is coming closer to carbon. So that means one length is increasing, bond length is increasing, another bond length is decreasing. They are actually in the opposite direction and we call it as anti-symmetric stretching. Okay, so these are two types of stretching, 1 and 2, symmetric and anti-symmetric. Now we'll go to bending, the second type. Bending, the exactly reverse of stretching will happen in the case of bending. That means in the case of bending, the length is going to remain absolutely same. There is no increase in bond length, there is no decrease in bond length. But what is changing? The bond angle is going to change. Angle is going to change. But length is going to remain absolutely same in the case of bending. That's a basic thing about bending. Now, bending is divided into subdivided two types, in-plane bending and out-of-plane bending. I hope the students understand what is meant by in-plane and what is meant by out-of-plane. So if you draw a circle on your board, if you draw a circle, it has got 360 degree. I can cut the circle by drawing a perpendicular vertical line passing through the center. I can cut the circle into two hemispheres. I can draw a horizontal line passing through the center. I can again cut the circle into two hemispheres. I have the freedom to cut the circle by drawing any lines at any angle which passing through the center. And each line is going to be a plane for me. When I am drawing a 100% vertical line, is a vertical plane. When I am drawing a 100% horizontal line, is a horizontal plane. And all other lines which are passing, they're all slanting planes at various different angles. Each one is a plane for me. Now you imagine all the students you are sitting in the classroom. There is a whiteboard hanging on the wall, and your classroom wall is 100% vertical plane. And the table in front of you, the writing table in front of you, maybe is 100% horizontal plane. Now imagine your CS2 methylene group is sitting on the board, and the board is 100% vertical plane. And So carbon is on that board, both the hydrogen atoms are also on the board. So during the motion, during the vibrations, all the three, carbon, one hydrogen, the second hydrogen, all atoms are going to be on the board only. Sitting on the board, they are going to vibrate in some way, and that's what you are going to see. But they are all in the same vertical plane. So those type of motions are known as in-plane bending motions. In plane, they are all remaining in the same plane, in plane. But there are certain motions where some of the atoms will remain on one particular plane and some of the atoms may go to a different plane. In that case, we say they are out of plane bending motions. Okay, so that is why it is divided into in plane and out of plane. And in plane is again divided into two types, scissoring motion and rocking motion. And everyone knows what is a scissor, what is a scissoring motion. All of us are using a scissor at home or in the office or the college, maybe for cutting a paper, for cutting a cloth, whatever it is. And the scissor has got two arms and there's a central pivot and two arms are there. So when you are cutting a paper with a scissor, how the arms are working, the arms will go apart and come together, go apart and come together. And in that process, it goes forward, and that is how we are able to cut it. So during the motion, the two arms are continuously coming closer and moving apart. Again, they are coming closer, they are moving apart. This is the motion of the two arms of a scissor. Exactly, if you consider the motion of both carbon-hydrogen bonds in a CH2 group, consider these are the two arms of a scissor. How they will act? They are coming, the hydrogen, both the hydrogens will come closer, again they will go apart. Again they will come closer, again they will go apart, like the two arms of a scissor, and that is why it is known as, and doing so, your carbon and both the hydrogens are remaining on the board, in plane. So it's called in plane, scissoring, bending motion. And there is one more in this, rocking. Everybody knows what is a rock dance. So two people are performing a rock dance. They are swinging either in one direction or the other direction. Maybe they are swinging to the left side or to the right side, but they are moving simultaneously. Both are turning, bending to one side or to the other side on simultaneously. So if you consider these two carbon-hydrogen bonds, they will be either swinging. Swinging means either they will be bending toward the left-hand side simultaneously, or they will be bending toward the right-hand side simultaneously, and that is called a rocking motion. But here also, all the three atoms, carbon, hydrogen, and hydrogen, they are all remaining on the boat, on the plane of the boat, and it's called in-plane rocking bending motion. So that is over. Now we are coming to the last one, that is out of plane. Here, some of the atoms are going to be a different plane from the original one. So now again, we are keeping the CH2 group on the board. And here we have got two different types. One is called twisting and one is called wagging. Now twisting, everyone knows what is meant by the meaning twisting. Suppose we are keeping two fingers together and I can twist my fingers. When I'm twisting my fingers, one finger will bend backwards and one finger will bend forward. Okay. So originally they were in the same plane. I am keeping two fingers close together in a vertical position. So it's a vertical plane. But when I am twisting my fingers, one finger is turning, bending backwards, and one finger is bending forward. And they are going to two different planes now from the original one. So similarly, you consider your carbon-hydrogen bonds as two fingers and carbon is at the center. So when twisting happens, what will happen? Carbon will remain on the board. One hydrogen will jump out of the board, it will bend towards you, and another hydrogen will bend toward the backside of the board. So that means these two hydrogen atoms have come to a totally different plane, whereas carbon is on the same plane, original plane. So it is called out of plane, twisting, bending vibration. And the last one is called wagging. Wagging means what? All are going to all the atoms are going to totally different planes here. See, both the hydrogens can bend towards you from the board, and carbon can bend to the backside of the board. That is one possibility. or the carbon can bend towards you and the hydrogens can bend to the other side, the back side of the bond. That means all the three atoms have gone to totally different planes. And that is why it's called out of plane, wagging, bending, vibration. So what is our conclusion? A molecule can undergo 6 different possible vibrations. Not necessary that all the vibrations have to take place. There are 6 possible vibrations: symmetric stretching, anti-symmetric stretching, in-plane scissoring, in-plane rocking, out-of-plane wagging, and out-of-plane twisting. Total 6 different possible vibrational motions are there in a molecule. And what is more important is each type of vibration may be able to absorb at multiple positions in the IR spectrum. That means if you are recording the spectrum from 4000 inverse centimeter to 400 inverse centimeter, that's a scan range. Each type of vibration may be able to absorb at multiple positions. Not that one vibration will absorb only at one point. It may be able to absorb at multiple points. And like that, there are 6 different vibrations. So you can imagine what will be the total permutations and combinations possible when a molecule is subjected to IR radiation. And that is precisely the reason why you are able to see so many absorption bands in an IR spectrum compared to a UV spectrum. Yesterday, you have seen some UV spectra I showed you. A very simple spectrum, very simple. Most of the time, it's a single band, broad band between 360 and 190. But when you look at an IR spectrum of a compound, you will see so many multiple absorption bands coming between 4000 and 400. And this is the reason why it is happening. Because there is so many possibilities of vibrations and the possibility of a single vibration absorbing at multiple points, multiple locations. And that is precisely the reason why you are able to get many different absorption bands. And for a sample, yesterday we spoke about UV, and today that was my first question to you. What is the condition for a sample to absorb UV? And when we know that it has to contain at least one chromophore. Unless and until there is a chromophore, the sample will not absorb UV. Similarly, when it comes to IR radiation also, for a sample to absorb IR radiation, there are 2 conditions. Unless and until these 2 conditions are fulfilled, the sample will not absorb IR radiation. It will be IR transparent. So what is condition number 1? I'll just read it and tell you. When the molecule is irradiated with electromagnetic radiation like an IR radiation, the energy of the light must be equal to the vibrational energy level difference within the molecule. So that means there has to be a match between these 2 energies. Energy of the incoming radiation and the vibrational energy level difference in the molecule. Okay, so each of the different vibrational modes give rise to a different absorption band. I will simplify this. The first thing, when the molecule, that means when you are, I told you at even normal conditions, a molecule, the chemical bond is not standing still. It is continuously vibrating with a certain frequency. And that is what is known as the fundamental vibrational frequency of the chemical bond. And when the IR radiation is coming and falling, the radiation also has got different frequencies. The frequencies of the incoming radiation and the vibrational frequency of the chemical bond, they have to match. If they match, a certain quantity of the energy will be absorbed. Otherwise, it will not be absorbed. It will just pass through. The sample will not. So this is condition number 1. Matching of frequencies. Condition number 1 for a sample to absorb IR radiation. There is one more condition for the sample to, and before that, so this is a simple equation: delta E vibration equal to H into C into W, where delta E vibration is the vibrational energy difference in the molecule, H is the Planck's constant, C is the speed of light, and W is the wave number in inverse centimeter. Okay, so for condition number 1, there is one more condition if a sample has to absorb IR. That is condition number 2 for IR energy absorption. A molecule must undergo a net change in the dipole moment. Very important. A molecule must undergo a net change in the dipole moment as a consequence of vibrational or rotational motions in order to absorb infrared radiation. So that means for a symmetrical molecule, suppose if the change in dipole moment is zero, there is no definite change in dipole moment, it is zero, then the sample will not absorb IR radiation. There has to be a definite change, net change in the dipole moment. Then only the sample, when it is subjected to IR radiation, then only the sample will absorb IR radiation. Otherwise, it will not be absorbed. The sample will become IR transparent. And so when a sample is absorbing IR radiation, when we talk about the intensity of absorption bands, when it is absorbing IR radiation, it is going to give you an absorption band. And many times you can see when you look at an IR spectrum, you will see some of the bands are very intense, some of the bands are medium intensity, and some of the bands are very, very less intense also. So the intensity of absorption bands is proportional to the square of the change of the dipole moment that is taking place during the vibration. The change in dipole moment is d mu by dr. That is the change in the dipole moment, where mu is the dipole moment, r is the internuclear distance. That is the distance between two connected atoms. That is the distance. R is the internuclear distance and mu is the dipole moment. And d mu by dr is the change in the dipole moment. And the intensity is directly proportional to your square of the change in dipole moment, d mu by dr square. That is the intensity. Okay. So if you, so what will happen if there is no change in the dipole moment, d mu by dr becomes zero. So that means not automatically your intensity becomes zero. That means your absorption is not taking place. A sample is not absorbing IR radiation. So that means simple terms, you can say the sample becomes IR transparent. Okay, so these two conditions are very, very important for a sample to absorb IR. And I will explain this in a very short thing with taking carbon dioxide as an example. Carbon dioxide CO2, one carbon atom and two hydrogen atoms. Okay. So oxygen compared to carbon is slightly more electronegative. So there is a charge separation. It becomes a dipole. Oxygen becomes slightly electronegative delta minus and carbon becomes slightly positive delta plus. Okay. And carbon dioxide can have two different vibrations. If you look at the symmetric vibration and anti-symmetric vibration. Stretching. I'm talking about stretching. Symmetric stretching vibration and anti-symmetric stretching vibration. So the first one on the right-hand side, you can see the symmetric stretching. When carbon dioxide undergoes symmetric stretching vibration, the symmetry of the molecule is maintained. That means there is no change in the dipole moment. And because of that, carbon dioxide under symmetric stretching mode, it is IR inactive. It will not absorb IR radiation under that mode. But when carbon dioxide undergoes an anti-symmetric stretching, you can see on the extreme right-hand side, there is a change in the definite change in the dipole moment. There's a definite change in the dipole moment. You can see in the slide. And because of that, carbon dioxide, when it undergoes asymmetric stretching, it absorbs IR radiation. I mean, those who are recording spectrum in FTIR, many times when you're recording the sample, you will see a very small peak coming around 2250 inverse centimeter. 20 to 50 inverse centimeter, you will normally see a very small peak. That is nothing but because of the atmospheric carbon dioxide. That peak is coming, and that's an asymmetric stretching vibrational peak of carbon dioxide. Okay, so dipole moment is simply two charges separated by a distance. That's a very simple definition. All the students know that dipole moment is simply two charges separated by a distance. It's a vector quantity. It has got both magnitude as well as direction. And mu is the dipole moment. Mu is equal to Q multiplied by R, where mu is the dipole moment, Q is the charge on the atom, and R is the distance between them. So that's a dipole moment. Okay. So now when you record the spectrum of a sample from 4000 to 400 inverse centimeter, and if I am going to cut the spectrum, By drawing a line at 1500 inverse centimeter, I can cut the spectrum into two parts. The second part is always known as the fingerprinting region. Second part is always known as the fingerprinting region. That's the most informative part of the spectrum. Very complex region of the infrared spectrum below 1500. See, 4000 to 1500 is the first part, and 1500 to 400 is the second part. The second part is called the fingerprint region. Most informative, maximum absorption bands will come there. You get a lot of information about the sample from the second part. And it is a characteristic of the molecule as a whole. And whatever vibrational bands, most of the vibrational bands you are going to observe in the second part, that's the fingerprint region, they're all predominantly because of bending vibrations. Very, very few stretching vibrations will come in the second part. Otherwise, they are mostly because of bending vibrations. But the bands you are going to see in the first part, between 4000 and 1500, they are all predominantly because of stretching vibrations. We'll see that an example here. We have recorded the spectrum of a compound between 4000 and 600. And we are cutting this spectrum at 1500 by dropping a line. So second part is fingerprinting region. You can see, you will see maximum number of bands coming there. They're all because of bending. And look at the first part, some 4000 to 1500. You will find lot of stretching vibrations, or sometimes this first part is also called stretching region of the spectrum. Stretching region. Nitrogen, hydrogen stretching, carbon, hydrogen stretching, oxygen, hydrogen stretching, carbon, oxygen double bond stretching, carbon, carbon double bond stretching. Lot of stretching vibrations are coming. And that is why it is also known as a stretching region of the spectrum. And the second part is called bending region of the spectrum, fingerprinting region of the spectrum, and where you will find maximum bending vibrational bands are appearing. And that is why it is known as the most informative region. Suppose if you look at some of the British pharmacopoeia monograms in the pharmaceutical analysis, they will be showing many of this IR spectrum right from 2000 downwards. So some 2000 to say 400 or something like that will be showing. So that is giving more importance to the fingerprinting region rather than the first half of the spectrum. These are band positions. Here I am going to, I'm showing a slide. There are three columns. The first column, I have shown some important functional groups. Second column, where the band is going to appear, that's called the band position. And the third column is the intensity. Okay. Some of the functional groups, a lot of functional groups I have written. I mean, for example, let us take a typical example, C double bond. Carbonyl functional group, C double, say very, very prominent functional group in IR spectrum, carbonyl functional, C double bond. And where it is going to appear? It can appear anywhere between 1670 to 1780. We are giving a band. We are giving a certain range, 1670 to 1780 inverse centimeter, anywhere it can come. Why? Because we are giving a band, because a carbonyl functional group can be provided by different types of compounds. A carboxylic acid also can give you a carbonyl group. A pure ketonic compound, they can give a carbonyl function. A aldehyde also can give a carbonyl function. Amide also can give carbonyl function. So there are various sources of carbonyl functional group from different types of compounds. And depending upon the type of compound, this carbonyl functional group can appear anywhere between 1670 to 1780 inverse. And last, you look at the intensity, it is going to be a very, very strong intensity absorption band. So any sample containing a carbonyl functional group will give very strong absorption band. So the intensity is also very important. So when you are looking at an IR spectrum, you have to please keep, this is an advice to students, please keep 3 points in mind. One is where the band is going to come. That is, the band position is very, very important. First of all, look at the band position. Second, look at the intensity. And what is the third factor you have to keep in mind? The shape of the band. Shape of the band is also equally important, because sometimes we can differentiate between two different compounds depending upon the shape. I will give an example also. Shape, when I say shape, means sometimes the peaks are very sharp sometimes the absorption bands are very broad also. And that also can give you sometimes a very important information. For example, if I'm going to give you a primary alcohol, which contains a OH group, and I'm also going to give maybe, or I'm going to give a carboxylic acid, which contains a OH, and I'm also giving you a primary amine, which contains an NH2 group. And if you record the spectrum, there is going to be a carbon-hydrogen stretching band in both, because I am sorry, I am giving an NH2 amine, NH2, and then I am going to give a carboxylic acid, ISI. So then so when you look at this, how will you, when both are going to absorb when you look at the carboxylic acid and amine, carboxylic acid, there got a OH stretching, oxygen, hydrogen stretching, and amine, there is a nitrogen, hydrogen stretching. Because one is an NH2 group, one is an OH group. Okay, so OH group, oxygen, hydrogen, and nitrogen, hydrogen stretching, the regions are going to be more or less very close to each other. So by only looking at the band position, it can come somewhere around 3000 approximately. I'm not giving the exact figure. Somewhere around 3000 or 3200 or 2900, 3100 region it can come. Oxygen, hydrogen as well as carbon, hydrogen. Oxygen, hydrogen as well as nitrogen, hydrogen. So by looking at the band position, you'll not be able to differentiate whether it is a amine or whether it is a OH containing compound. Then what is the differentiating factor? You look at the shape of the band. In the case of a primary amine, the shape is going to be very sharp, whereas other compound, the band is going to be broader. So one is a broad peak, one is a sharp peak. So there is a definite change in the shape of the band, and that itself is an indicator to what type of a compound it is. So you can differentiate. So shape of the band is important, intensity of the band is important, position of the band is important. So all the 3 points you have to keep in mind while you are trying to assess a compound based on the IR spectrum. So this is a formaldehyde gas phase spectrum, formaldehyde. So you can clearly see carbon hydrogen stretching, CS2 asymmetric stretching coming at 2850, CS2 symmetric stretching coming at 2785. Now look at the carbonyl function here, because it contains a carbonyl functional group, formaldehyde, aldehyde. 1750, you can see it is the most intense peak, very, very intense peak coming at 1750 inverse centimeter. So it's a carbonyl function. Then we have got other CS2 scissoring and CS2 rocking and other things, swagging and all. So this is how we, basically to interpret an IR spectrum, it is not a difficult task, it's not a rocket science, but you have to work towards that. Start with a known compound, record the spectrum. You know the compound is known to you, try to assign the bands to certain functional groups in the compound. Thereby you can practice, and by practicing you will be able to master the technique of IR interpretation. I know in many times in industry also people don't identify. People only take a standard sample and a normal sample and a reference standard, record the spectrum, they overlap it through the software, and all the peaks are matching. Then they say the sample is identified and passed. This is what actually happens in many other industries also. Now let us, for your understanding, what is the difference between a dispersive IR and FTIR. First of all, dispersive IR is not available today. Every manufacturer has turned over to switched over to FTIR, but this is only for your understanding. Dispersive IR contains too many moving parts, so there was a lot of wear and tear problem, mechanical movement, whereas FTIR has got a relatively simple optical system. Affected by starlight, dispersive IR affected by starlight. Yesterday we know what is starlight, any unwanted radiation coming to the detector, and in that case the sensitivity will go down. So dispersive IR, we were facing that problem, affected by starlight. Whereas in the case of FTIR, negligible starlight effect. That means you are sure of sensitivity. In the case of dispersive IR, lower signal to noise ratio and resolution, and FTIR excellent signal to noise resolution. Because signal to noise ratio, I told you, because that is the one which actually shows the sensitivity of an equipment. Today, an equipment is actually evaluated on the basis of signal to noise ratio. Higher the signal to noise ratio, higher the sensitivity. And in the case of FTR, you get high signal to noise ratio. That means you get a very high sensitivity, and you are also getting very good resolution. Resolution is extremely important. If resolution is lost, you are losing information about the sample. So resolution is very, very important. And the most important difference between these two techniques is, that's the essence. In the case of dispersive IR, single wavelength at a time, and FTR, all wavelengths at a time. So this means what? That's the most important difference between these two. And because of that, dispersive IR is called a sequential scanning technique, and FTR is called a simultaneous scanning technique. So what does it mean? So if you are recording the spectrum from 4000 to 400 inverse centimeter using a dispersive IR, olden time, when I started my career, this FTR was not there at all. I used to work on a dispersive IR. So the detector will be able to see only one wavelength at a time. It will look at 4000, then it will come to 3999, then it will come to 3998. So like that, one by one, it has to come to 400. That was taking long time. A single scan of the equipment, single scan of the sample using a dispersive IR was taking approximately 12 to 15 minutes, long waiting period. Whereas in the case of FTIR, the detector is able to see all wavelengths simultaneously. From 4000 to 400, it can look at the wavelength simultaneously. You can see all together, and that is why it is known as simultaneous scanning. And what is the advantage as a user? In less than a minute's time, I can take multiple scans of the sample. So I can 25 scans, I can take 36 scans, I can take 49 scans, I can take 64 scans, like that. Multiple scans I can take, and how much time it takes? About less than a minute's time. As against almost 15 minutes for a single scan in dispersive IR. That's a major advantage of a FTIR over a dispersive IR. But luckily for you people, today dispersive IR is not available, or everyone is offering, every manufacturer is offering only an FTR equipment. So in the case of dispersive IR, you have to separate all the wavelengths, because 4000 to 400 inverse centimeter, different frequencies are there in the incoming radiation, and that is a polychromatic light. Yesterday we discussed about that, UV, polychromatic light. Polychromatic light is a light containing different wavelengths, different frequencies. And in the case of dispersive IR, since the detector can only see one wavelength at a time, we have to separate all these wavelengths using a monochromator. That means a dispersive IR was using a monochromator. We were having a diffraction grating as a monochromator inside a dispersive IR. But now today's FTIR, we are not going to disperse, because no need of dispersion, because the detector can see all the wavelengths simultaneously. So we need not separate it. So there is no monochromator in an FTIR. There is no monochromator in FTIR. It's a very important thing. But monochromator is replaced by an equipment which is called an interferometer. In place of a monochromator, FTIR contains an interferometer, and the student should know how an interferometer works. That's the most critical part of your FTIR. That's what I'm going to discuss in few slides. So it's very, very important to understand how the FTIR functions and how you are getting a spectrum, FTIR spectrum, and what is the main function, what is the main responsibility of the interferometer inside an FTIR. Maybe a little difficult to understand, but I'll try to make it very simple as possible. So this is a optical diagram of a dispersive IR. I'm just skipping that. And this is an optical diagram of FTR also. I'm skipping this because you will be able to see a much better diagram after a few slides, which you will be able to understand it better. And before going to interferometer, there is a light source. Yesterday we spoke about D2 lamp, which was offering UV light. Today here also, IR also contains a light source. There are different types of light sources available, and in our equipment we are using a ceramic source, a small ceramic bead which is heated to almost around 2000 degrees centigrade, and then it starts emitting IR radiation. Okay, So that is the infrared source. So we have a infrared light source inside, and this light is emitting IR radiation, and this IR radiation has got different frequencies. And this radiation is directly coming to the interferometer because there is no monochromator, absolutely no monochromator. But in place of a monochromator, we have a interferometer. And how the interferometer is going to function, that's the most critical part of today's discussion. I'm going to come to that. So there are different types of interferometers: a Michelson interferometer, Fabry-Perot interferometer, Sagnac interferometer. Out of this, Michelson interferometer is supposed to be the most popular interferometer, and that's the one we are going to discuss because it's the most important, most popular, most familiar interferometer that is used by most of the manufacturers. So we are going to discuss Michelson interferometer a little bit in detail. And what is a Michelson interferometer? It consists of two plane mirrors at right angles to each other. So there are two plane mirrors in the interferometer, and they are kept at right angles to each other, 90 degree. Okay, and now in between these two plane mirrors, there is a beam splitter. You can understand right from the word beam splitter. That means there is something which is going to split the light beam. That is why it's called beam splitter. The light beam is coming to this, and it is going to split it, and it is called a beam splitter. And the beam splitter is placed between these two mirrors. In the next diagram, it will be very easy for you to understand. So what is the job of the beam splitter? The beam splitter is going to split the incoming radiation into two equal halves. Okay, half portion, 50% of the incoming radiation is reflected to one mirror, which is called a fixed mirror, because it cannot move. The position is fixed. That is why it's called a fixed mirror. And the remaining 50% of the incoming radiation is getting transmitted to the beam splitter, and it goes to the second mirror, which is called a moving mirror. Why is it called a moving mirror? It can slightly move. If the position is not fixed, that is called a moving mirror. So basically, the interferometer is working on the principle of moving mirror mechanism. So this is the basic thing you have to imagine. Two mirrors are there. One mirror is fixed and one mirror can move. They are at right angles to each other, 90 degrees. And in between these two moving mirrors, there is a small part which is called a beam splitter. And the light from the light source is coming and falling on the beam splitter, and it is going to split it into two equal halves. 50% is getting reflected to the fixed mirror. Remaining 50% is getting transmitted to the moving mirror. We'll see how it happens. Okay. So instead of using a monochromator, so we are not going to use a monochromator at all in an FTR. Instead of using a monochromator, IR radiation after passing through the sample compartment can be analyzed using a Michelson interferometer. Okay, so Michelson interferometer consists of a fixed mirror, a moving mirror, and a beam splitter. Very simple mechanism, very simple alignment. And the radiation from the source is split into two equal parts by the beam splitter. And one half is reflected to the fixed mirror, while the other half is transmitted to the moving mirror. And after reflection, and when they are going to two different mirrors, but they are all mirrors. Fixed mirror is a mirror, moving mirror is also a mirror. So when the light is coming and falling on a mirror, it gets reflected back. So after reflection, the two beams are again coming back to the beam splitter, and they are coming and combining, recombining. So after reflection, the two beams are recombined at the beam splitter. And the two beams interact at any particular wavelength, either constructively or destructively, depending upon the difference in the optical path. This I am going to discuss in another 2-3 slides for you to understand. That's a very critical part. Okay. So this is the Michelson interferometer. Now this slide is very easy for you to understand. On the right-hand side, extreme right-hand side, we have a source of light, that's IR source, and it is emitting IR radiation when it is heated. And this light is coming and falling on the beam splitter. Beam splitter is nothing but two plates of potassium bromide, two plates of rectangular plates of potassium bromide, and it can be circular also. So two plates of potassium bromide, And in between these two potassium bromide plates, you can see a very thin pink-colored film. That's a germanium film. So a very thin germanium film is sandwiched between two potassium bromide plates, and that is acting as a beam splitter. Okay, actual splitting is because of the germanium film. Potassium bromide is acting as a holder for the film. That's all. Potassium bromide pellet is not splitting. The splitting is taken place by the film, germanium film. It has got its inherent property, and there has to be something, a thin film. There has to be a holder. So we are keeping a potassium bromide holder because the potassium bromide is a transparent material. That's the reason why we are keeping a potassium bromide plate, using a potassium bromide plate. So when the light is coming and falling on the beam splitter, you can see the beam is divided into two equal halves. 50% is getting reflected from the surface. It goes to a fixed mirror. You can see the fixed mirror there at the top. And remaining 50% is passing through the beam splitter. It is coming to a moving mirror on the left-hand side. And that mirror can slightly move forward and backward through a very small distance at a constant velocity. So what will happen? And when these two light beams are going to two different mirrors, they again get reflected back. They come back and they meet each other. So if the distance between these two mirrors from the beam splitter, they are equal. That means both the path lengths are equal. That means the fixed mirror and the moving mirror, they are at equal distance from the beam splitter. That means the optical path lengths are same. When these two light beams are going to the mirror and coming back, they will meet each other. That means there is going to be an enhancement in the intensity. And when these two beams are coming together, and it will result in a constructive interference pattern. Two light beams are interfering with each other in a constructive manner, the constructive interference pattern. So there is an enhancement in the intensity, and this combined beam can pass through the sample compartment, and then from there it will directly go to the detector. So there is absolutely no separation. All the wavelengths will be seen by the detector simultaneously. So now what will happen now? This is the position when this is the situation where both the mirrors are at equal distance from the beam splitter. Now in the second instance, you imagine your moving mirror is slightly gone backward. Either it can go backward or forward, slightly gone backward. So now in this case, the path length, there is a difference in the path length between the beam splitter and the moving mirror. Whereas fixed mirror, it is not moving, it is constant, it's standing without any movement. So that is always a constant. That distance is always a constant. But moving mirror has gone backwards. So there is an increase in the path length. So that means that particular light beam which is going to the moving mirror now has to travel a slightly more distance. Whereas the other light beam which is going to fixed mirror, that path length is always constant, it will come back. And the second light beam which has gone to the moving mirror will take a little longer time to come back because it has to travel a longer distance now. So when they are coming back, they are not meeting each other. That means they will result in a destructive interference pattern. So by changing the distance of the movement of the moving mirror, we are actually creating a difference in the path length. And this difference in the path length is ultimately resulting in either a constructive interference or a destructive interference. Whenever there is a constructive interference, there is an enhancement of intensity. And whenever there is a destructive interference, there is a decrease in the intensity. Either means at one point the intensity will increase and one point the intensity will decrease. This is going to be getting repeated cyclically. And that is ultimately giving a sinusoidal motion, sinusoidal type of wave we are going to get from the beams. When the light is finally coming to the detector, it is a sinusoidal wave that is coming. One point there is an intensity increase, one point there is a intensity decrease. So that is what is discussed here. The intensity of the emerging radiation is getting modulated in a sinusoidal manner. When the sinusoidal manner, you can see when it is going a wave motion, you imagine like a wave motion. At one point it is going to a maximum point, the next point is coming to a minimum point. Again, it is going to a maximum point, it's coming to a minimum point. So it is getting continuously repeated in a cyclical manner. And that's a sinusoidal model. It's getting modulated in a sinusoidal manner. In the case of a broadband infrared source, because your infrared light contains lot of frequencies, it is not a single frequency, lot of frequencies are there. The emerging beam, so each frequency is going to undergo a modulation. So when the emerging beam is a very, very complex mixture of modulated frequencies, which after passing through the sample compartment will be focused onto the detector. And the detector signal is sampled. The signal coming from the detector is to be sampled at very, very precise interval using the during the mirror scan. So when the mirror is continuously moving backward and forward, there is a intensity increase or there is a intensity decrease in the detector signal. And that is to be very, very precisely sampled, very precisely measured when the moving mirror is moving through a small distance backward or forward. And so both the sampling rate means the sampling of the detector response, detector signal, that is to be very precisely measured. That's a sampling rate. So both the sampling rate and the mirror velocity are precisely controlled and measured by an independent reference beam. So we also have other than the IR radiation light, IR source, we also have a reference light inside. And this reference light is provided inside an FTIR for precisely this reason, for measuring the sampling rate and the mirror velocity, moving mirror velocity. And what is the source what we are using? It is a modulated monochromatic beam of light. Essentially, it is a helium neon laser light. So we have a laser beam inside, we have a laser light inside. And so there is a separate laser gun, and that is emitting this laser light. What is the quality of a laser? It is a single wavelength radiation. It's a monochromatic radiation. Okay, so that is used as a reference light inside the FTR for measuring the sample signal, detector signal intensity, as well as the velocity of the moving mirror. Okay, so the detector, the laser is emitted by a laser gun, and laser also has got a separate detector. There is a laser detector. We have got an IR detector, we have got a laser detector inside the system. The resulting signal, whatever the signal is that is going to come from the detector, is called an interferogram. And interferogram contains all the information required to reconstruct the spectrum using a mathematical process known as Fourier transformation, FT. So interferogram is nothing but a set of data collected in the time domain. Now, if you look at the interferogram, whatever sample you have got, when you keep it in the FTR, you will get the same type of interferogram. That means I cannot differentiate one compound from another compound by looking at the interferogram, because both the compounds are going to give me the same shape of interferogram, same type of interferogram. So that means I am not able to understand anything by looking at the interferogram, because it is a set of data collected in the time domain. And what we are used to? We are used to looking at a data in the frequency domain. If I am getting a data in the frequency domain, I can understand this. So the data that is remaining in the time domain is to be converted into the data into frequency domain, and that is done by a mathematical equation which is known as Fourier transformation. FT is nothing but a mathematical treatment, so that it is converting the time domain data into frequency domain data, so that when we get the frequency domain data, we can understand what are the bands, what is it because of, what is it due to. All this information will be coming through, and by looking at the data in the, so when FT is applied to IR, it becomes FTIR. When FT is applied to your NMR data, it becomes FT-NMR. Okay, when we are trying to, so FT is nothing but a transformation from one set of data to another set of data, from time domain data to frequency domain data. Now, if you what actually happens when the moving mirror is moving? Look at this slide. We have a fixed mirror at the top. It's represented by C, and you have a moving mirror. Okay, and that is initially both the mirrors are at equal distance. The distance between moving mirror and the beam splitter, and the distance between the fixed mirror and the beam splitter, they are equal. That means when the light is getting split, and when they come into these two mirrors, when the lights are getting reflected back, and when they come to a beam splitter again, they will be combining together because the distance is same, the velocity is same. So this position where the moving mirror and the fixed mirror are at equal distance from the beam splitter, that particular position is known as ZPD, zero path difference position. It is called ZPD, zero path difference position. And whenever it is a zero path position difference, it creates a constructive interference pattern. Okay, now you imagine the mirror is going to, moving mirror is going to slightly move backward. Either it can come forward or backward. This is only for to make you understand. It is the moving mirror is slightly going backward by a distance of lambda by 4, quarter lambda. Lambda is the wavelength, quarter lambda for any wavelength. So what will happen now in this particular case? The moving mirror has gone backward by a distance of lambda by 4. The light which is coming to the moving mirror now has to travel an extra distance. Now the distance between the moving mirror, what is the path length now? Path length difference now. That is the distance from the beam splitter to the moving mirror and back to the beam splitter. It is lambda by 4 plus lambda by 4. So it has to now it has to travel an extra distance lambda by 4. Okay. So what will happen now? So the difference will be 2 into lambda by 4 because the light has to travel extra lambda by 4 2 times when it is coming to moving mirror, and when it is coming back to beam splitter, it is traveling extra lambda by 4 distance. So 2 times lambda by 4, 2 into lambda by 4, that means lambda by 2. So that means both the light beams, the light beam which is going to fixed mirror and the light beam which has come to moving mirror, there is a difference in the path length by lambda by 2, 180 degree out of phase. Both the light beams are 180 degree out of phase. Whenever two light beams are out of phase, it creates a destructive interference pattern, and it creates a decrease in the intensity or a minimum intensity point. Okay, now this is one position. You can see that the first moment from D1 to D2, D1 is the ZPD position. It has come to D2, that is, it has traveled a distance of lambda by 4. So that now the light beam has to travel 2 times lambda by 4 multiplied by 2, lambda by 2. Both the light beams are 180 degree out of phase and creating a destructive interference pattern. Now one more position I have shown, D3 position, means it has gone one more lambda by 4 backward. So now how much it has gone? Lambda by 4 plus lambda by 4, lambda by 2. And then now what is the light beam has to travel lambda by 2 distance 2 times. Means while coming from beam splitter to mirror and back from mirror to beam splitter. So 2 into lambda by 2 is lambda. So that means both the light beams are again in phase. And whenever in phase, there is an increase in intensity. And that's why you see at the bottom of the moving mirror, ZPD, there is a maximum intensity point. D2 position, there is a minimum intensity point. Again, D3 position, there is a maximum intensity point. So like that, depending upon whether these two light beams are in position, in phase or out of phase, there will be maximum points or minimum points getting repeated in a cyclical manner. Okay, so that is what you can see here. I have shown 3 different light waves. The first 2 are in phase, and when these 2 beams are in phase, depending upon the difference in the optical path, it will always give rise to a maximum point that is called a bright zone. And look at the light beam at the top, at the bottom, and that is 180 degree out of phase. And whenever there is an out of phase, it is going to create a decrease in the intensity that is called a dark zone. So depending upon the movement of the moving mirror, you will be getting multiple bright zones, that is maximum points, or multiple dark zones, that will be minimum points. So that is why it is getting modulated. It's a sinusoidal modulated waveform that is coming to the detector. And it's a very complex thing because there are so many frequencies and each frequency is undergoing modulation. And it's a very complex thing that is coming, and that is what is you can see here. And ultimately, what the detector is going to give you is an interferogram. And interferogram is what you see, and every compound, every sample, what you're going to keep in the FTR is going to give the same type of interferogram. And you cannot understand anything from this unless, and this is a data collected in the time domain. And if we convert this into frequency domain, we can see that, we can understand that. Okay, now we can just show this. This is the light source. IR radiation is coming from the light source. It is coming to the beam splitter, and the beam splitter is splitting into two. One is going to fixed mirror, one is coming to moving mirror. Initially, they are at equal distance. They are coming back and recombining at the beam splitter, passing through the sample compartment and going to the detector. And the detector is going to give an interferogram. That is what you see at the bottom, and that is a set of data in the time domain. Now, through the software, FT is applied, Fourier transformation is applied, and this data is converted into a frequency-based data. That is what you see on the right-hand side. That's your normal spectrum. So when you are actually keeping the sample, when you're actually doing the analysis, you will be on the screen, you'll be getting the normal spectrum. You will not find the interferogram coming on the screen, but that is already there inside. That's already there in the system, because the conversion has already been taken place internally, and what you see and what is shown on the screen of your equipment is the normal spectrum. But if you really want to see an interferogram, you can take it because that is already available in the system. Okay. Now let us see what are the basic components of an FTR. So I hope all the students understood how the interference pattern is created and what is the function of the moving mirror, and how the interference pattern is created by creating a difference in the optical path length between the moving mirror and the fixed mirror. That's a very essence of understanding FTIR. The rest of things are very easy. Basic components of FTIR, you have got a light source. You also have a laser source, and then there's an interferometer. Both the light source, IR light, as well as the laser light will be passing through the interferometer. And once it is coming out of the interferometer, the laser light is taken out and detected by a separate laser detector. Only your IR light will pass through the sample compartment, and then whatever is coming from the sample compartment will go to the detector, and the detector signal will be processed by your PC and software, and you can output. Okay, there are what type of detectors what we can use. Once upon a time, we are using thermocouples. Today, nobody is using a thermocouple as a detector for IR because it is less sensitive, very slow response. These are some of the drawbacks. But today, we have got two different types of detectors that are widely used. One is called a pyroelectric detector, which is coming under the heading thermal detector. And I will tell you what is the thermal difference between these two. And then we have got photoconducting detector, which is known as a quantum detector. So there are two different popular detectors. One is a thermal detector and one is a quantum detector that can be used. But most of the applications, we don't go for a quantum detector. Quantum detector is used only if for some very, very critical applications, very critical analysis, where the intensity of the IR radiation is very weak. Then only we use a quantum detector for those type of analysis. Otherwise, normal applications, we use only a thermal detector. And we'll see what is the detector. Okay. So thermocouple, of course, I'm skipping this, very slow response and less sensitive. So nobody is using a thermocouple nowadays. One is then we are coming to photoconducting detector. It's an example of a quantum detector. And what is a quantum detector? It's a semiconductor detector using a material in which the incident IR light will cause will produce a change in the electrical conductivity. Because of the IR radiation coming and falling on the detector, the electrical conductivity of the material will be changed. This is a very basic working principle of a quantum detector. And they are quite expensive also. For example, one example is a mercury cadmium telluride detector, MCD detector, which we normally use in a IR microscope. Because IR microscope, we are analyzing some very, very difficult samples, and you normally go for a quantum detector like MCT, mercury cadmium telluride detector. Okay. Otherwise, normal applications, we don't use that because MCD detector also requires liquid nitrogen cooling. So generally, photoconducting detector has got a very wide range, 10,000 inverse centimeter to it can even come to around 300 inverse centimeter. Can be operated at room temperature. Mercury cadmium telluride photoconducting detector is used for mid-IR and far IR detection, and used only for very high sensitivity for IR measurements. So normal applications, we don't use a photoconducting detector. It's only for very, very selected and specific applications. But what is more widely used is a pyroelectric detector. Please understand, most of the instruments will be a pyroelectric detector. Okay, it is a thermal detector. It's an example of a thermal detector. And what is a thermal detector doing? It is converting infrared energy to heat radiation, heat energy, and which is then converted into electrical energy by piezoelectric effect. So initial IR radiation, when it is coming and falling on the detector material, it is initially converted to IR radiation is converted to heat energy, and this heat energy is converted to electrical energy by pyroelectric effect. And very simple sentence, I don't want to go into details. Pyroelectric effect is a phenomenon in which the surface charge or polarization of a dielectric material changes due to the variation in surface temperature. Because IR, it's a heat radiation. So when it is coming and falling on the material, there can be surface temperature variations. So wherever there is a variation in the surface temperature, that induces some surface charge or polarization in a dielectric material. And that induces a electric current. And that is what a pyroelectric material does. And we are using a pyroelectric material as a detector for FTIR. And it is widely used in mid-IR region. And a very popular material is a triglycine sulfate. It's nothing but a crystal. It's a chemical material, triglycine sulfate. And triglycine sulfate is a wonderful pyroelectric material. Okay. And whenever it is subjected to IR radiation, the change in the surface charge results in the TGS material when the IR radiation is coming and heating it up. So pyroelectric effect is related to the incident radiant power, and it has also got a very, very wide spectral range. Okay. Now, the TGS material, when you talk about TGS material, triglycine sulfate, it is a pyroelectric material. Now, what we are using in our equipment is we have slightly modified this material, because every pyroelectric detector has got a certain temperature. It's called Curie temperature. It's a very specific temperature, Curie temperature. And what is Curie temperature? Simple definition of Curie temperature. Curie temperature is the temperature at which a ferromagnetic material is getting converted to paramagnetic material. That's if you know, that is the definition. Curie temperature of a material is the temperature at which a ferromagnetic material is getting converted to paramagnetic material. Okay. Now that means the efficiency of conversion of heat energy to electrical energy will be maximum at Curie point temperature. And if the Curie point temperature goes up, the temperature of the material goes beyond the Curie point temperature, the conversion efficiency, heat energy to electrical energy conversion efficiency will reduce. That means the sensitivity of the detector material will come down. So to avoid this, we have converted this TGS material into DLA TGS material, deuterated L-alanine coated triglycine sulfate. Why it is done is, a normal TGS material has got a Curie temperature of somewhere around 48 degrees. If I remember correctly, around 48 degrees centigrade is the normal Curie point temperature of a TGS material. By any chance, if your instrument is continuously on and if the temperature of the material, detector material goes beyond 48 degrees, the detector response will come down, sensitivity will come down. By converting TGS into DLA TGS, triglycine sulfate is getting converted to deuterated L-alanine coated triglycine sulfate. The Curie temperature is gone to 61 degrees centigrade, approximately 61 or 62 degrees centigrade. That means you're 100% sure, even if the instrument is on continuously for a longer period of time, this temperature will never be crossed and your detector sensitivity will never reduce. That is why we have converted this TGS material into DLA TGS material. Advantages of pyroelectric material, it's an excellent signal to noise ratio. That means sensitivity. Frequency response is very good and the response is also very, very fast. Okay. Advantages of using FTIR, multiplex advantage, all these we have discussed, but these are some different names I'll tell you. Multiplex advantage, aperture advantage, laser reference advantage, and the application advantage. What is multiplex advantage? I told you because the FTIR is able to see all the wavelengths at a time, whereas a dispersive IR, the detector is able to look at one wavelength at a time. That means sequential scanning and FTR, it is simultaneous scanning. Detector is able to see all the wavelengths at a time. And the plus point for you is the speed of analysis. It becomes much, much faster compared to dispersive IR. That is what is known as multiplex advantage. Aperture advantage is better utilization of quality of light. Results in improving light intensity and signal to noise ratio. Compared to an dispersive IR, in the case of FTIR, more amount of light is coming and falling on the detector, and that will increase the sensitivity and intensity. So that results in improving light intensity and signal to noise ratio. So several tens to 100 times higher energy throughput compared to a dispersive IR. That means compared to a dispersive IR, the amount of light that is coming to the detector is almost 10 times or even much more than that. More amount of light intensity is coming to the detector, which ultimately results in a much better signal to noise ratio. That means much better sensitivity. And laser reference advantage, I already told you why we are using a laser, because we have to precisely measure the detector response and the moving mirror velocity. And so that is the reason why we are able to, we are using a laser reference light inside an FTIR. And constant periodicity of laser provide a uniform sine wave pattern, which is good for analog digital conversion. And wave number accuracy of spectrum is also ensured. So when you record the spectrum, your x-axis is always the wave number axis in centimeter -1, inverse centimeter. And that should be very precisely calibrated. And that is also done with the help of a laser reference light. So that's the importance of laser reference advantage. Application advantage, we have very, very difficult applications can be carried out without any problem using an FTIR. And some of these applications we are not able to do using a dispersive IR many, many years back. High sensitivity measurements are possible, easy to measure low transmittance samples, measurement of a very small area. Suppose I give you an example like a tablet in pharmaceutical manufacturing. Suppose there is a very black, it's a very tiny microscopic black spot on the tablet. You do not know whether it is an impurity sticking, an external impurity sticking to the tablet, or whether it's something coming from the tablet itself. You do not know. At the same time, you may not be even able to take it out. It's a minute spot. But if you have a microscope connected to an FTIR, we can keep the tablet itself without any sample preparation. You can focus the light on the spot very, very precisely and take the spectrum. And we can even, many times, we can magnify that. So very small area measurement is possible. Measurement of thin layer film on a surface. High-speed measurement is possible. And multi-layer packaging material, they can be used. So they can be analyzed and identified. So a lot of advantages for different types of applications. And Fourier transform infrared spectroscopy, especially when you are using an FTIR, is a widely used qualitative identification technique. Compounds can be characterized by identifying the functional groups present in the sample. Unlike UV spectra, IR spectra differ considerably for different compounds. That's a major differentiation between UV and IR. UV different compounds may give similar type of spectra, but IR, every compound is going to give a different spectra. Quantification is possible, but though it is not widely used. Very few people use IR for quantification. Can be used for the analysis of solids, liquids, and gases, whereas UV can be used only for solids and liquids, not for gases. But here we can do even gas samples also. Before you embark upon an IR analysis, certain information is required. What is objective? You should be very clear about the objective of your analysis. What is the objective of analysis? Little bit of background information about the sample is absolutely required, essential. Solubility of the sample is important. Hardness of the sample is important. Some samples are very hard, some samples are very soft. You should know about the hardness of sample, otherwise you may spoil some of the crystals which we are coming to. Degradation of a, so whether the sample is a degraded material, whether it's a sample is a reactive material. So some information is always required before you start with an analysis. And different types of samples and what are the suitable techniques that you can employ in IR. Solid samples. It can be a powder sample, it can be a solid sample, it can be a sticky sample. There are different methods for that. Nujol mulling, KBR pelletization, DRS method. Dr. Vikram was referring to a drift analysis. DRS method, here we are trying to talk about diffuse reflectance. DRS method, ATR, AEM. AEM is a microscope. All these can be used for solid. What is Nujol mulling? I'll just spend a minute on this. Many people, I don't know whether students are aware of this. Suppose you have got a very sticky material like a wax material or something which is sticking to some surface. Though if I have to analyze this sample, I will employ a Nujol mulling technique. What I will do, Nujol is what? Nujol is nothing but spectroscopy grade liquid paraffin. It's a water white material, 100% transparent, little viscous hydrocarbon, hydrocarbon. It's a spectroscopy grade liquid paraffin. It's a hydrocarbon. And you take a very small quantity of the sticky material in a small pestle and mortar, add 1 or 2 drops of Nujol, which is liquid paraffin, and mix it well, make it a fine paste, and take a small drop of this paste on a crystal, either a sodium chloride crystal or a potassium permanganate crystal. What are the crystals that can be used? We are going to see, and then put on one crystal and put another crystal over that, and then this paste is going to spread like a thin film, and then you can keep this crystal in a sample holder and you can record the spectrum of the sample. So it is basically Nujol mulling is used for those type of samples only. A sticky sample, very pasty sample type of material. KBR pelletization can be used for powder sample. That was the method which was used very widely by industry, even pharmaceutical industry. You have to make a potassium bromide pellet. You have to take about 1 or 2 milligram of sample, add about 100 milligram of dry potassium bromide, spectroscopic potassium bromide, and mix it well. That process known as trituration. And after that, take this mixture in a dye. And the dye is to be vacuated, connected to a vacuum pump, and then you have to apply pressure. Normally, we apply around 10 to 15 atmospheric pressure on that and keep it for about 15 minutes time. And after that time, you release the vacuum, release the pressure, open the dye, and if you have prepared it properly, you will get a 13 millimeter diameter circular disc, which looks like a piece of glass. This process known as KBR pelletization method. At the same is a very difficult process also, because it is highly subjective. Different people making pellet of the same sample, the quality of pellet can be different depending upon the individual. It's a very, very difficult process, time consuming. And that was a process which was widely employed in pharmaceutical industry till very recently. But now we have got certain attachments called DRS method, ATR method, where we can directly measure the powder sample without making a potassium bromide pellet. And these methods have become official in United States Pharmacopoeia. USP 34, all these attachments have become official. United States Pharmacopoeial methods, all these attachments are approved now. So it has become very, very easy. Liquids, We have got different types of samples, demountable cell, fixed path length cell, and you can also use an ATR method for liquid samples and gases. We have got different gas cells are available. You have to fill the gas inside the cell, and the cell is kept inside the sample compartment, and you can measure record the spectrum of a gaseous sample. Reflecting surface, suppose a coating on a glass, coating on a metal, coating on a metallic surface or a mirror. All these type of coatings can be studied. They are all called reflecting surfaces. We have got a separate attachment for that. That's called specular reflectance attachment. Plastic container or drum, suppose you have got a 1,000-liter syntax tank on the terrace of a building for storing water. And it's a polymeric material. Syntax tank is a water tank is made of a polymeric material. And it is getting continuously exposed to UV sunlight. And because of UV radiation sunlight, this polymer also can undergo degradation. And you want to study whether it has undergone degradation or not. And you can do it by IR. But how will you sample a 1,000-liter or 2,000-liter drum? You have got a very small accessory with which you can do this. I will show you that. And multi-layer packaging material, especially very, very important in pharmaceutical industry. We have got a microscope that can be connected to NFTIR. Okay, transmission method, potassium bromide pelletization method. That is the one which was used for a very long time. Nujol method can be used for sticky material, or liquid film method means you can dissolve the powder material, solid material in a suitable solvent, make a solution, and keep it on a pellet. Pellet means a crystal, like potassium bromide crystal or sodium chloride. So many crystals available, and keep it under an IR lamp. The solvent will go off, and this will give a very thin film, and that's what is called a thin film method. Otherwise, is a liquid sample, also sometimes a viscous liquid sample. You can just spread it as a thin film on a crystal and dry it under an IR lamp, and then you can record the spectrum. That's called a film method, liquid film method, or Nujol method. This is a caffeine powder, transmission spectrum of caffeine powder. We prepared a potassium bromide pellet. We have prepared 45 scans. The scan was repeated 45 times, and the time taken was about 1 minute time. And when you are taking more number of scans, and when you go for averaging, your signal will increase, noise will decrease. That means signal to noise ratio will increase, your sensitivity will increase. So, okay. Now, when you're coming to liquid film method, liquid samples, there are 3 different types of cells. One is called a demountable cell that is normally used for qualitative analysis, only for identification. Demountable sample means in the cells can be, there are 2 cells in the demountable cell. Cell means 2 crystals, sorry, 2 crystals, the demountable cell. Crystal is either it will be rectangular crystal or it will be circular crystal. And these crystals can be made of different types of materials: sodium chloride, potassium bromide, cesium iodide, zinc selenide. Lot of materials are available. And you can open this. You can put 1 drop of a liquid on 1 crystal and put another crystal over that. Slightly press it, so it will spread like a thin film. And there's a holder. You can record the qualitatively. You can record the spectrum of the liquid sample using demountable cell. Demountable cell means the crystals can be separated. You can open the cell, and the crystals can be taken out separately. Like after the use, you can wash it, and you have to keep it under. You have to keep it in a desiccator. You keep it always under desiccation, because many of the cells are very, very susceptible to moisture. Okay. Now there is something called sealed liquid cell. Sealed liquid cell is normally used for semi-quantitative analysis. Sometimes people are even using it for qualitative analysis, but it is mainly meant for semi-quantitative analysis, where you can change the path length by using different types of spacers. Spacer means thickness, a certain, you can see a spacer, something between 2 plates, you keep a spacer, and depending upon the thickness of spacer, there is a path length difference between the crystals. So that's called a sealed liquid cell. And you can again open the cell, remove the crystals, and remove the spacer also, but that is only for semi-quantitative work. But if you really want to do a quantitative analysis, you have to go for a fixed thickness cell. Fixed thickness cell means you cannot open the cell. It is totally fixed by the manufacturer. You cannot open it. It's only for 100% quantitative analysis. So use the fixed thickness cell for quantitative analysis, where you cannot open the cell, and use a demountable cell for quantitative analysis, where you can open the cell, take out the crystals, and wash it and all. And even for fixed thickness cell also, there is a washing procedure without opening the cell. So fixed thickness cell is for quantitative analysis, and demountable cell is for qualitative analysis, and sealed liquid cell is for semi-quantitative analysis. And these are some of the window materials. When I say window, it is a crystal. I am referring to a crystal as window material. And that is why, because normally we have a window in the room. That window is actually, when you open the window, the sunlight is coming into the room. Similarly, when I am using a window, a crystal, this window or the crystal is allowing the IR radiation to pass through and come to the sample compartment and fall on the sample. Okay. So what type of windows? And when there are lot of crystals available that can be used as window materials. So what are the things you have to remember? Wave number. Every window has got a certain wave number range. And you should know what is the wave number range you are going to use for your sample. Accordingly, you have to select the crystal. Chemical properties of the sample, chemical properties of the crystal, this should be known to you. Physical properties of the materials. As I told you, some of the materials are very hard, some are very soft. That also you should know. And finally, cost of the material. There are a lot of crystals that are available: sodium chloride, potassium bromide, cesium bromide, calcium iodide, calcium fluoride, zinc selenide, KRS5, germanium, diamond. A lot of things are there. And every window material, every crystal has got a certain wave number range also. And the refractive index is also different. Refractive is also an important factor. You will see, I will tell you what is it during one of the slides going forward. Okay. So, but please remember, you cannot use crystals like sodium chloride or potassium bromide or cesium iodide for samples containing large amount of water or aqueous samples, because all these materials are highly water soluble. They can be used for non-aqueous samples. But aqueous samples don't use materials like crystals like sodium chloride, potassium bromide and all, because that is spoil the crystal. For that, then you have to use certain materials which are totally insoluble in water. Calcium fluoride, silver chloride, KRS5, zinc selenide, these are all totally insoluble in water, and they can be used for non-aqueous samples. And there is a very popular window material crystal is called KRS5. It is nothing but 1:1 mixture of thallium bromide and thallium iodide. It's a wonderful window material. It has got a wide range. It can go down to even 250 inverse centimeter, completely covering your mid-air range, insoluble in water. You should be careful only about two things. One is, you should not use a very highly alkaline pH solutions. Means anything have pH beyond 10 or beyond 11, you should not use. That can attack the material. And solutions of phosphates. These are the two things you should avoid with this material. Otherwise, it can be used for aqueous samples, non-aqueous samples. You can even wash it with water, nothing happens. And this is a thallium compound. So people consider it as slightly harmful if there is a cut on your finger or something. So in that case, don't use your bare hand. You can use a gloves, put a gloves and then handle this material. But otherwise, it's a very good window, very good crystal. But at the same time, it is a little costly also. Quantitation, of course, this you have seen yesterday, Beer-Lambert's law. We can do quantitative analysis by IR, but very, very few users are using IR quantitation. But IR can be used for quantitative, absolutely no problem. I am going to show an example for a quantitative analysis. It's a standard method. Determination of determination of oil and grease in water. Determination of dispersed oil and grease in water is a very important parameter for water quality and safety measurement. And we can do it it's an official method. And this is to be done by IR. And we should have a reference material for this quantification. And what's the reference material we are going to make? It's a mixture of 25% benzene, 37.5% isooctane, and 37.5% hexadecane. That's a standard material. And then we are going to measure the absorbance between 3,200 and 2,700 inverse centimeter, and the peak absorbance at peak maximum at 2,926 inverse centimeter is going to be measured. And you can see a calibration, and we have prepared a different standard material right from 1 ppm to 40 ppm. And for all the standards, we are measuring the absorbance at 2926 inverse centimeter. And we are going to create a calibration curve, multi-point calibration curve. After this, we can measure the actual sample and find out what is the oil and grease content in water. It's an official method, and we have actually we have actually optimized this method in our lab. And coming to some of the last part of the discussion, some of the optional accessories for FTIR. And these are all reflectance techniques. Number one is attenuated total reflectance techniques on an ATR. Diffuse reflectance, when you talk about drift analysis, diffuse reflectance spectroscopy, there is a DRS attachment, and specular reflectance for coatings on metals, coatings on glass, reflectance, reflecting surfaces. We have got a separate attachment. So there are three popular attachments: ATR, DRS, and specular reflectance. And we can also add a microscope. We can also connect a microscope to an FTIR. We'll see a few examples that also. And the most popular ATR is called attenuated total reflectance technique. There are two different types. One is called a horizontal type, one is called a vertical type. Horizontal type attenuated total reflectance spectroscopy, and vertical type attenuated total reflectance spectroscopy. Horizontal type is more important. Horizontal type is more widely used. Horizontal type is more versatile compared to vertical type. So what are the features of horizontal type ATR? Sample pre-treatment is not necessary. You can keep the sample as it is and record the spectrum. And non-destructive analysis. After completing the analysis, you can take the sample back. Nothing, no destruction. Information on the sample surface can be obtained. And once you record the spectrum with the ATR, there is a small correction that is called an ATR correction that is to be applied to the software. Don't forget that. And what type of samples you can analyze by horizontal ATR? Very large number of samples can be analyzed. Liquid samples, gel samples, solid samples like paper, cloth, yarn, powder, drug samples, then cosmetic materials, packaging materials, hair analysis. Lot of samples can be analyzed by horizontal ATR. Okay, so that is why it has become more important, more versatile, more popular compared to vertical. But vertical ATR is not that popular because your sample has to be in the vertical position. That is why it is called a vertical ATR. Whereas in the case of horizontal ATR, sample has to be in the horizontal position. There is a 10 centimeter crystal in horizontal ATR. There are different types of crystals that can be used. And your sample is to be kept on the crystal in a horizontal position. So because of that, you can use a powder sample, you can use a liquid sample, you can use a cream sample, lotion, anything. Whereas in the case of a vertical ATR, the crystal is in the vertical position. So sample has also to be in the vertical position. Because of that, you cannot use a powder sample. You cannot analyze a liquid sample. Only you can analyze for thin film samples. A cable, a tire material, rubber material, polymeric films, those type of packaging materials, only those type of samples which can stand in a vertical position only can be analyzed by vertical. So vertical ATR is not very popular. Okay. ATR spectrum measurement, the sample is held in contact with a prism made of highly refractive index material. The incident angle of IR beam is larger than the critical angle, and hence the IR beam is totally reflected by the interface between the sample and the prism. I will tell this with the help of this. See, there is a, what you see at the in between, there's light blue color, that's a prism, that's a crystal. There are different types of crystal that can be used. And your sample is on the crystal. Only the requirement is sample has to be in total contact with the prism. There should not be an air gap. And the light beam is coming to the crystal. the angle of incidence is more than critical angle. What is the critical angle? I think students should know the answer. What is the critical angle? Critical angle is that angle of incidence for which the angle of refraction is 90 degree. That is called critical angle. That means for a certain angle of incidence, if the angle of refraction is 90 degree, that angle of incidence is called critical angle. And if your incident angle is more than this critical angle, the light will undergo total internal reflection between the sample and the crystal. That's called TIR, total internal reflection, or it is also called multiple internal reflection, MIR. You can see that in the slide. The light is getting transmitted from, is going from the crystal to the sample, coming back to the crystal, again going to the sample, again coming back to crystal. That is getting repeated multiple times. So that means it is getting internally reflected between the crystal and the sample multiple times. And that is process known as a multiple internal reflection process. And finally it comes out and it goes to the detector. Okay, so this is, and the you can see at the bottom I have shown a DP. DP is the penetration depth. The IR radiation is penetrating the sample to a very, very small distance. That's called a penetration depth. Okay, and this there is a mathematical equation also. We can calculate the penetration depth. So let us I'm just skipping it. If I want to analyze to differentiate between two different, this is a food application, two different beverages, drinks, beverages, beverage A and beverage B. Compositions are different. If suppose I record the spectrum of these two beverages in UV, probably it will give me a very same type of UV spectrum. I will not be able to differentiate between beverage A and beverage B. But if I record the spectrum of these two beverages using an HATR in FTIR, my IR spectra are going to be totally different. I can differentiate between beverage A and beverage B. There is a clear-cut difference and extra peaks are coming. So there are samples can be differentiated between these two by recording the IR spectrum, and this is performed with the help of a HATR. Okay, this is a cosmetic application. Especially when you are using winter time, people apply a lot of moisturizing lotion and all on the face and your skin. Why? Because you want to keep your skin moist, and you have to keep your skin in a hydrated way, because otherwise loss of moisture, skin becomes very dry. So you have to keep your skin as smooth as possible. You have to hydrate your skin, and that is what exactly a lotion does. A cold cream or a cold lotion is actually hydrating your skin. So there are a lot of lotions available, lot of brands available in the market. Suppose if you want to find out which one is a more effective lotion as compared to another one, you can use a HATR analysis, human skin analysis by HATR. This data was created in Shimatsu, Japan, and we have used HATR. And it's what is done is you have taken your palm of your hand and just kept it on the HATR crystal in FTR and record the spectrum. That's the topmost one. The red colored spectrum is untreated palm. That's the spectrum of the human skin. And the middle one, green colored one, is after this you have wiped your finger with your palm with ethanol, ethyl alcohol, wiped it well, again kept the finger on the crystal, you get another spectrum, that is palm wiped with ethanol. And the last one you see at the bottom, the blue colored spectrum, what you have done is we have applied the milky lotion on the palm, kept it for a certain time, and then wiped it off, and then again kept the finger, again kept the palm, and you got the spectrum, that is palm after applying milky lotion. And if you look at the spectrum, all the three spectra, you feel they're all same, but there are minute differences. And you need a special software to study this. You require a peak split software for this. And when you're actually applying peak split software in this can be deconvoluted, and then what information you get. There is amide peak, there is a ratio. What we are trying to find out is the ratio of amide to water. Amide is coming from your human skin and water is coming from your lotion. And there is a specific ratio of amide to water. Okay. And the one which is going to give you a highest ratio of amide to water is going to be a most effective skin, a most effective lotion. Untreated palm, it is 0.55. After wiping it with methanol, because your skin has become dry, water is gone, most of it, so the ratio has become 0.12. And then you applied milky lotion A, it has given a very high ratio 0.68 compared to second lotion, and that is giving only 0.43. So that means the lotion A is found to be more effective lotion as a moisturizing one, because it hydrates your skin to a larger extent compared to the second lotion. So that is how we have evaluated this. It's a purely cosmetic application using FTIR. Biodiesel blends with HATR. You can see the petroleum, diesel, and FAME. Normally, biodiesel is basically formulated by incorporating fatty acid methyl esters of vegetable oils into petroleum. And you can even see how much of FAME content is present in a biodiesel blend. You can even do quantitative analysis. And this was recorded by an HATR. And this variable vertical, is called variable ATR, variable attenuated total reflectance. As I told you, it is not very popular because the crystal is in the vertical position. The sample also has to be in the vertical position, but it is used in a few industries where people are in, especially packaging materials, cable manufacturer, tire manufacturer, where you can cut the sample as a very thin slice and it can stand in the vertical position along with the crystal. Only for those type of samples you can do a vertical ATR. But otherwise, it cannot be used for normal powder samples or liquid samples or any other cosmetics or lotions. So those type of samples cannot be analyzed by. So it is not very popular, but very most popular is HATR. Okay. Now, once you record the spectrum, you have to do a correction to the software. That's called an ATR correction. Once you do the correction, whatever after correction, you will get a spectrum which is very, very similar to a normal transmission spectrum. Then effect of refractive index. Refractive index of the crystal should be always more than the refractive index of the sample. Please keep in mind. So any sample containing carbon black has got a very high refractive index. It's somewhere around 3.6 or 3.7, roughly around more than 3. And most of the crystals have got a refractive index less than that. And if the refractive index of the crystal is less than the refractive index of the sample, you will get a very bad quality spectrum. This is a spectrum of acrylonitrile butadiene rubber containing carbon black as a reinforcement material. We have recorded the spectrum using a KRS5 window crystal. That is what is at the top. You see, it's a very bad quality spectrum. No peaks are seen. But we used the germanium prism. We got a good quality spectrum because germanium is only the crystal which is having refractive index more than carbon black. Germanium refractive index, I suppose it is more than 4, definitely more than carbon black. So whenever we are supplying this to some rubber industry or any polymer industry where people are analyzing materials containing carbon black, we always advise them to use a germanium prism. Germanium prism is the only prism which is having higher carbon refractive index compared to carbon black. We also have diamond ATR. Diamond ATR ensures intimate contact samples and greatly reduces sample size requirement. The why diamond ATR is required is, especially when I told you one thing in the beginning, for requirement of IR analysis, you should know the hardness of the sample, physical properties of sample. There can be some very hard samples, like a polymer bead, very, very hard sample. You cannot ensure a proper contact between the sample and the prism because it is a polymeric bead, it's a circular bead. You have to really press it to create a proper contact. But because the material is so hard, your crystal will break. If you apply pressure, your zinc selenide or germanium or KRS5, these are all light crystals, they will break. So you cannot use those type of crystals. Then in that case, what is the solution? Go for a diamond ATR. And everyone knows diamond is the hardest material. So here what you see, the yellow color is the primary crystal. It can be KRS5 or zinc selenide. And over which you can see a slight blue color, that's a pure diamond we are keeping. And you are keeping the sample on the diamond. And then we are applying pressure to make the sample flat. And because diamond is so hard, nothing happens to diamond. And the light beam will come. It is called a single reflectance diamond ATR. It's called a single bounce ATR, because there is only one. You can see the light path coming from the source, going to the material and coming down and going back to the detector. It's called a single bounce. And here again, I'm showing an example of a same material, caffeine powder, analyzed on a diamond ATR. And you are getting exactly the same spectrum as if you have prepared a normal potassium bromide pellet. You are getting the same quality of spectrum. At the same time, it's much easy. And how much sample quantity you want? You hardly require about 1 or 2 milligrams of sample. If it's a liquid sample, you need a tiny drop of the sample. The sample quantity is much reduced in the case of a diamond ATR. So diamond ATR also has become very, very popular. This is a differentiation of different geological example. Geological samples for diamond ATR. Different types of quartz material, SiO2, depending upon the position from the place where it is mined, location of the mines, the location, the quality of SiO2, the quartz can be different. And different types of quartz material can be differentiated by recording the spectrum using a diamond ATR. It's a purely geological application. And we are coming to some pharmaceutical application, identification of pharmaceutical excipients by ATR. Hypromellose acetate succinate is a very prominent pharmaceutical excipient used for enteric coatings. It is also used as a carrier for solid dispersions to facilitate miscibility and bioavailability of poorly soluble API. Official compendia such as Japanese Pharmacopoeia and US National Formulary NF, they describe the qualitative identification of this material by FTR with ATR technique. So you can see the structure of hypromellose acetate succinate, and we have analyzed it by normal ATR, diamond ATR, and you can get the spectrum, you can identify the compound. Okay, this is a typical example of another ATR application, a contaminant on a pharmaceutical tablet. After manufacturing a tablet, on the left-hand side, you can see there is a red circle. This slight yellow patch is shown, and we have circled it in a red color, lighted. We do not know whether it is an external impurity coming and sticking on the tablet, or whether it is something which has come from the formulation itself, maybe because of improper mixing and blending. Something has come out on the surface and it has got segregated. We do not know. So we want to know whether it is an external impurity or whether it is something internally present and that has come and segregated on the surface because of improper blending and mixing. We have used an ATR technique for that. What we did, we kept the tablet as it is, and then we focused the beam on that yellow patch. We got a spectrum. Right-hand side top spectrum, you can see the black colored spectrum is the spectrum because of that yellow patch. We went for a library search. Library gave us two options, two possibilities. One is the green one, that can be acetyl salicylic acid. And the red one, it can be acetaminophen. So there are two possibilities. Now we do not know what is this, whether it is acetyl salicylic acid or acetaminophen. So what we did for confirmation, using a very tiny blade, we slightly scraped off that yellow part. We got few particles of the yellow material. Again, we analyzed that powder as it is. We remove the tablet, we keep that powder, scraped off powder, hardly 2-3 milligram, and record the spectrum. Left-hand side, bottom, you can see the black color is because of powder. And when we went for a library search, it was identified as acetaminophen. And then one more experiment we did, we scraped off little powder from the clean portion, not the yellow patch, from the other side, other part of the tablet, took a little powder, and that also analyzed. It is known as acetyl salicylic acid. So the yellow patch, what we have seen, is because of acetaminophen, which was a part of the formulation itself. It was not an external impurity, It was one of the ingredients in the tablet formulation itself, maybe because it has come to the surface and got segregated because of maybe improper blending. They will have to modify the blending operation, that is manufacturing operation. So it's a very quick way of identifying an impurity on a pharmaceutical tablet. We are coming to the diffuse reflectance measurement, what normally known as drift analysis. DRS method is applicable to almost all samples, especially for powder samples that can be pulverized. Pulverized means you will have to mix it with potassium bromide. You should be able to grind it in a small mortar and pestle. We are supposed to triturate the sample with potassium bromide. That is basically what pulverization, as a mixing with a small, tiny pestle and mortar. And once you mix it, you can take the sample mixture, that is a sample plus potassium bromide, directly in the DRS attachment. And what is the proportion? You take about 2 milligrams of powder sample and you take about 100 milligrams of potassium bromide, pure dry spectroscopy grade potassium bromide, mix it well and take in the sample. There's a small sample cups available. So you can see some small sample cups, and you can keep the sample hardly some few milligrams, hardly 3 or 4 milligrams only will go inside that sample cup. And the sample cup can be kept in the DRS, diffuse reflectance attachment. And that is what you see on the right hand side, diffuse reflectance attachment. And the sample cups are also shown below. And then this will sit in the sample compartment, and then you can record the diffuse reflectance spectrum of the material. And that is what is basically called a drift analysis. So normally, once you prepare a diffuse reflectance spectrum, you need to convert it to normal transmission spectrum by a mathematical conversion. That is known as Kubel-Kalman conversion. It is to be applied to the software. So Kubel-Kalman conversion, which is a mathematical conversion, is converting the diffuse reflectance spectrum of the material into a quantitative spectrum, which is very, very similar to the transmission spectrum. So whenever you are using a DRS, diffuse reflectance study, don't forget to apply the Kubel-Kalman conversion after getting the spectrum. It can be done to the software. Some of the examples, some polymeric material and used by DRS attachment. And then we had gone for library search. It was identified as phenol, nonyl phenol resin. You can even go for library. There are a lot of optional libraries available for FDR, but you have to purchase it. And this another material, polybutyl acrylate, and you can identify provided you have the polymer library, which you have purchased along with the FDR. And this is what I was talking about, SiC sampler, silicon carbide sampler, for very, very difficult materials. Like I gave an example. On the terrace of our building, there's about 2,000 liter syntax tank storing water. It's a polymeric material formulated and is getting continuously exposed to sunlight, UV radiation, and it can undergo degradation also. How fast the degradation can take place will depend upon what is the formulation, what is the antioxidants added to the formulation, all those. So you can, how will you sample the material? So you can use this accessory. You can go and just rub it on the surface of the tank a few times. And there is a abrasive material, that is what is shown as a black disc here. That's a sandpaper disc. It's called abrasive. It's a silicon carbide material. So when you are rubbing it, because it is an abrasive material, few particles of the polymer tank will stick to this. Come back to the lab, keep this abrasive disc on the DRS attachment, and you can record the spectrum. This is a DRS of a polyethylene tank before and after use. It may be a 1,000 liter tank or a 5,000 liter tank. The left hand side, what you see is the brand new tank, and the right hand side, it has undergone oxidation because of continuous exposure to sunlight. But how fast this oxidation can take place will depend upon the formulation of the material. Okay. Now, specular reflectance method suitable for coating thin films on metals, and only the requirement is the thickness of the film should be more than 1 micron. That's only. And you can analyze different types of samples wherever there is a coating of a film on a glass, coating of a film on a metal, and provided the coating is more than 1 micron. And this is the attachment. This is called a specular reflectance measurement attachment. And this is how it looks like. It is exactly like a DRS attachment. And this also will sit inside the sample compartment. And And once you record the specular reflections on material, you have to again apply a correction factor. A correction factor which is known as Kramer-Kronig conversion, another mathematical conversion. And Kramer-Kronig conversion is actually converting a specular reflectance spectrum into a normal transmission spectrum. So don't forget, because you can see the importance of this. What you see, the two IR spectra, the top one is IR spectrum of a PVC film on a resin material before application of Kramer-Kronig conversion. And once we apply this conversion, Kramer-Kronig conversion to the software, you get a normal transmission spectrum, what you see at the bottom. There's a normal spectrum which we can interpret, which we can understand. So that's important. And finally, we are coming to the last one, microscope. Possible to, you can attach a microscope to the FTIR, possible to measure microscopic samples as small as 10 micron in size. Very easy operation, used to determine contaminants on electrical contact points, fiber chips, thin layer of multi-layer packaging material, especially in pharmaceutical packaging, polymorphism study in pharmaceutical drugs, a lot of forensic applications, a lot of things can be done by. It's a very, very versatile equipment. The only thing is microscope, the cost of microscope is much more than the cost of an FTIR itself. This is how it looks like. You can see the on the extreme right hand side, what you see is the microscope. That's an external attachment. You have to connect the microscope with the FTIR with the help of a interface. And then you can do a lot of wonderful applications. Lot of applications are possible. And there are different types of studies. Transmission studies possible, reflection studies possible, ATR studies possible. This is a typical example of a pharmaceutical packaging with a 3-layer packaging material. If you look at the film, you feel it's a single layer, but actually it is a combination of 3 different layers. They're compressed together, a layer A, B, and C. And with the help of a microscope, we can identify what are these layers. A is found out to be nylon, B is polypropylene, and C is polyethylene. And even we can find out the thickness of each layer. So many microns, that also can be done with the help of a micro. We have customers working in FMCG industry as well as in pharmaceutical packaging industry using our microscope and FTIR. And this is a silicone grease coated on a medical syringe. Something which is slightly sticking on the tip of the syringe. We cannot even extract it. What we did, we kept the syringe as it is on the platform of the microscope, and we identified it as a very silicone grease. A bit of silicone grease was sticking to the needle. And any silicone material can be identified by a very prominent peak, SiO(Si) band, silicon oxygen silicon band, which will come around between about 1000 and 1100 inverse centimeter. You can get a very prominent peak of silicon oxygen silicon. And finally, conclusion, accessories solve different analytical problems. Accessories save a lot of your time. Not much of a training is required. Not much of sample preparation is involved. And the most popular accessories are, one is horizontal ATR, one is diffuse reflectance. I will add one more, which I have not shown, sorry. It is also diamond ATR. So I will consider there are 3 more very important accessories. One is horizontal ATR, one is diffuse reflectance attachment, DRS attachment for drift analysis, and one is your diamond ATR, single bonds diamond ATR. These 3 are very, very popular in applications. And these are some of the models. Just this is IR affinity, which works in mid-IR region. And this is another very compact IR. It's called IR Spirit. And you can take it in hand and then you can move around also. It's that light, IR Spirit. And it has got a dedicated ATR also, which is called QATRS. And that's very popular. I mean, a lot of users are using these equipments. And with this, I come to the last slide is the questions for tomorrow. I think all students can take this. Number 1, I will read it out. You can take a photo also. You can just note down what is the major difference between a dispersive IR and FTR. Question number 1 for tomorrow morning session. How is the interference pattern generated in an FTIR? Number 3, what is the difference between a debondable cell and a fixed path length cell? What type of a detector is commonly used in FTIR? Last one is why FTR quantification is little difficult as compared to UV quantification. Very simple questions. I hope you have all noted down this. So tomorrow, before I start with my thermoanalytical techniques, I will spend 5 minutes on these questions and anybody can answer as today what you did. Okay. Can I change this slide, madam? I mean, students have noted these questions.
Yes, sir, please.
Okay. That is the last slide. I will thank you once again very much for being with me for almost more than 2 hours. And I will hand over this to my colleague Amol. And after his short session, we can have a question answer session.
Yes.
Okay.
Yes, sir.
Over to Amol. I will stop sharing my screen.
Yes, sir. Thank you, sir. Sir,
Yeah, you can show the
hello?
video, 2 minutes video. Yeah.
Can you see my video?
We can see the screen. All of you can see.
Yes, yes.
Yeah.
Yes. Okay. Now I am starting the video. For only we have
minutes.
newly model like IR Spirit. So this is small video for you.
You can run the video, Amol.
Yes. Can you see?
Yeah.
Yes.
Yes, Amol.
Yes.
We can't see any voice associated with it. No.
Amol, what is the audio?
IR Spirit.
You probably have to share the video or share the audio of the computer if you,
Amol, start because no sound is coming.
You have to share the video or audio of the computer.
In the screen share option, when you click on the share screen, a window will appear. At the bottom of the window, you can see the share my audio with video like that. You just select that one, then audio will come.
Or maybe you can click on the view options on the top of the screen and you can share the computer audio.
Yeah, computer audio. You can close this one and share again.
Amol, you can close this, you can start from beginning.
Yes. Yes, sir. Yes, sir. Yes.
Because no sound is coming.
I think he's using his phone.
Okay. Now you are able to see?
Sir, are you wearing earphones?
Screen is coming.
Okay.
No, if Amul sir is wearing earphones, we can't hear audio.
Okay. I will again
Yes.
share. Yes. Just a minute.
Your audio has to be on.
Okay. Maybe 1 minute.
Yesterday it was there, Amol.
Yes, sir.
For you, yesterday it was there, but today that sound is not coming, audio.
Yes. Okay. Okay. Voice is coming?
No.
It's okay.
Now?
We can also see without audio.
We can see it.
Yes.
Yeah.
Yes.
Yeah, we can see without audio.
Without audio, you can see, yeah.
Yeah.
That's a fixed path length cell. ATR.
Okay, thank you for watching this video. This is a very nice video. Recently we have introduced IR Spirit. Can you see my screen?
Yeah, we can.
Yes, yes, sir. Thank you, sir, for giving the nice information about the FTI principle, applications, and the instrumentation part also. Today, in this my session, small introduction about the various models which are used in the FTR for the from the Simarzu, and its accessories. What are the accessories, and what will be the sample we can analyze on this FTR by using the Shimadzu accessories. Also, the software part, the how to get the spectrum of the sample on the FTR. We can just monitor the how we can take the spectrum of the sample. So there are many models in the FTR, Shimadzu FTR, but recently we are running models are like IR Spirit, IR Affinity, and IR Tracer. These are the most popular FTR models running on the Shimadzu models. The newly launched FTR is a IR Spirit model, which is a very compact model, having the very lightweight, and we can easily transport to one place to another place, and it required very small space for the accommodation. But whenever you are using the FTR, we ensure that the few points or a few cares precautions to be taken, like humidity and temperature. The humidity for these all the FTR, it's not below the more than 60, and the temperature is around the ambient temperature or the below the 24 degrees Celsius. 21 to 24 degrees Celsius is sufficient for the for the FTR instrument. So take care the humidity will not be exceed. If the humidity will be exceed, then it will be affect on the beam splitter, because a beam splitter in the FTR, the main heart of the FTR is a beam splitter. And FTR beam splitter is made up of the germanium coated KBR. So as soon as KBR is a hygroscopic material, if moisture quantity or humidity will be increased, it may chances to get beam splitter may get breakdown. So humidity factor may play important role. So we have to control humidity by using dehumidifier, which is inbuilt in the instrument, or we can put silica packs in backside of the instrument, or in the top of the instrument, which one space is there for all the instruments. So for air spirit, it it will cover the mid air range, like range from 350 to 7800 centimeter inverse. Ideally we are running the spectrum in mid air region, range from 400 to 4000 centimeter inverse. When we are using FTR with the ATR, so we are recommended that you have to use the range from 650 to 4000 centimeter inverse. And weight of this instrument IR spirit is a very lightweight, around 8 kg, 8 kg, around 8 to 8.5 kg weight is there. So very lightweight is there. A signal to noise ratio around 30,000 is to 1, which is the highest in its class. Maximum resolution for this IR spirit is a 0.9 to 16, but we are recommended, or by default we are using 4 centimeter inverse as a maximum resolution. If the resolution we are increased from 4 to zero 0.9, zero 0.9 is a maximum resolution. If we are using analysis, we are doing analysis in 0.9 centimeter, automatically resolution will be increased, but automatically noise of the sample or spectrum get increased. So to reduce this, to avoid this noise, we are recommending to run the sample in 4 centimeter inverse resolution.
Amal, I will make a point. I'll make a point here.
Yes, sir.
For
Yes,
the participants. Most of the powder samples, the resolution of 4 inverse centimeter is more than sufficient. You require a resolution less than, when you talk about resolution 2, resolution 1 and all, these are all required normally for gas samples. Otherwise, for normal liquid samples and powder samples, a very satisfactory resolution you can get by 4 inverse centimeter resolution. And that's why people use only 4 inverse centimeter resolution for solid samples and liquid samples. And resolution as low as 1 and less than 1 and all is required only for gas samples.
Yes, right. Then laser, in this IR spirit, laser is used as semiconductor laser. And previously in IR spirit or IR tracer, there is a laser is a helium neon laser they are using. But in this IR spirit, they are using semiconductor laser. Light source is the same like ceramic source, as sir has explained. The ceramic source, which is a very having a very good life shelf life is there for the light source. Detector, in this model, detectors are to use like DLA TGS, like deuterated L-alanine triglycine sulfate, or lithium tantalate. There lithium tantalate has a signal to noise ratio low as compared to DLA TGS. So DLA TGS has a more signal to noise ratio. Then our second model is a IR affinity. IR affinity is much bigger than as compared with the IR spirit. Is a size is very big, and weight also very big. It has covered the range from mid IR region, but it has a major factor that resolution power. Resolution power is start from 16 to 0.5. It has a high resolution power. And one more difference in that laser here it has used helium neon laser. And detector it has a detector is a DLA TGS. IR spirit also compatible for the liquid, solid and gas sample, but in IR spirit we can use only liquid and solid sample, not gas sample. With the help of IR affinity, we can analyze the liquid, gas, and solid sample also. And this IR affinity model can compatible with the that external microscope analysis that we can use to check the thin film layers or the thickness of the film thin layers. We can analyze by using the IR affinity. Then third model is IR tracer. IR tracer having the range in normally it come with the 350 to 7,800 means mid region, but with the optional we can get extended with the range can cover with the 12,500 to 240 centimeter inverse. And the major factor as compared with those both model, the signal to noise ratio is very high, around 60,000 to 1, and maximum resolution power also it has very high, 0.2 up to 0.25 centimeter we can go with the help of this IR tracer model. Here multiple detectors.
I'll add one point, Amol.
Yes,
IR
yes.
tracer, IR affinity and IR spirit can only work in the mid-IR range. Whereas IR tracer can cover all the three ranges. It can cover NIR, mid-IR and far IR. That's the importance of IR tracer. It is a very costly equipment, it's a very high-end equipment. And unless and until you have applications in NIR and FIR, there is no need of going for IR tracer because this is a very expensive equipment. It can cover the entire IR region, NIR plus MIR plus FIR. Whereas affinity and tracer can only cover mid-IR region.
Yes, sir. Yes. And detector by default, it has a detector DLA TGS, but optional MCT detector, mercury cadmium telluride detector we can use for the microscope. Whenever we are using microscope with the IR tracer, we have to use MCT detector for the thin film analysis or the thickness of the thin film analysis. That time you can use the MCT detector. As well as if we want to use to run the sample in near IR region, so in gas detector, indium gallium arsenide detector we can use, but this MCT and in gas detector are optional whenever we are using microscope or we want to run the sample in near IR region, so that time we can use this detector. By default, DLA TGS detector is inbuilt on this IR tracer. So for this three instrument, we can run by the software. The software name is a Lab Solution IR. With Lab Solution IR is a compliance software. We can compliance software is compliant with the 21st CFR Part 11 means electronic data and electronic signature. It's compatible with the electronic signature and electronic data recording. So with the help of IR Lab Solution IR, it same like look like a UV Lab Solution UV. It has multiple options, same like UV, like spectrum, quantitation, photometric, time course. But in IR, only we are using spectrum and quantitation. These two tabs majorly we are using for the analysis of sample in FTIR. In spectrum mode, we are run the sample like solid, liquid, gas with the help of different accessories. So in spectrum, we can set the how much analysis of the number of scan or detector we are using. So and quantitation we are using unknown like unknown concentration of the sample we can find out by the running the set of the concentration with increasing order and create the calibration curve and run the unknown sample. We get the exactly a peak height or intensity of unknown sample. By the help of this peak height or intensity, we can calculate the unknown concentration of the sample with the help of calibration graph. For spectrum analysis, we have to spectrum analysis we have to click on the lab solutions so IR software, and this window will be open. IR solution window will be open. Then we have to select spectrum tab. As soon as we are open the spectrum tab, this spectrum analysis window will be open. So first we have to, after opening the spectrum window, we have to initialize the instrument. We have to connect our software to the instrument. So in instrument tab, after clicking the instrument tab, one option is that initialize. As soon as we have clicked that initialize, automatically instrument get connected with the software and do the initialize parameter. Then check whether it's connected well, or check all the alignment and setting very properly or not. Then after alignment, we have to run the software for the spectrum. For same like a UV, before we are taking the run the sample, we have to take the baseline correction. Here we have to take background correction or baseline correction by using only if we are using ATR. In general, we are using taking the sample analysis or run the sample analysis on ATR. We have to put in sample compartment of FTR without any putting in solvent or anything. You have to take the background of air if your sample is as such. If your sample is diluting in any other solvent like acetone, ethanol, or any other material, like, so you have to take background with that solvent. After taking the background is completion. We have to put our sample, minimum quantity of sample on the crystal or diamond crystal, which is which covered by the sample only. Don't need to put excess of sample because the crystal part is very small. So we have to cover only that much part is, then apply the torque is applied by the sample holder, and it cover by whole sample is cover the diamond ATR. Then run the sample. We can get the spectra. Before they run the sample or run the background, we have to set the method parameter. So for method parameter, here method parameter we have to set like measuring mode like percentage transmitter. Here we are using absorption or transmission. For the absorption of transmission, we can get selected or select any one of these. Then apodization, we have to select half Genzel. Apodization is a window that collection of the spectra in specific region or specific region. We have to select the spectrum. The apodization is selected. The number of scan we have to mention over 45. If this is a 45 is a by default number of scan. If you want to reduce your noise, as soon as you have increased the number of scan, automatically your noise will be get reduced. So we have recommend to get number of scan more than 60. More than 60. If you are taking more than 60, automatically your multiple scanning get increased, and automatically your background noise get reduced. So 45 is a by default, but we will recommend that you have take more than 45 number of scan till 100, no issue. Then resolution, you can set the resolution as 4 centimeter inverse by default. It is sufficient for the analysis of sample, any sample. Then you have to set the range. If you want to run the sample in mid-IR region, so you can set the range from 4000 to 400 centimeter inverse. Beam splitter and detector and mirror speed is by default. So no need to change in that beam splitter, detector and mirror speed. If you are using a detector, external detector, like when you are using IR affinity with the microscope, then detector will be changed. The standard option is replaced by the external detector. And beam splitter, beam also same, no issue when you are using external device like microscope. After this set the parameter, we have to doing with the baseline or background correction. Background correction, after the run the background correction, you have to put your sample in the sample compartment, like sample place into the diamond ATR and run the sample. We get the spectrum of that sample. After they run the sample, we get the spectrum look like this. So after they run the sample, we have to get label the peaks. So there are multiple options in IR solution, lab solution IR. Like here, at the top of the software, there is a manipulation option is there. We can select here the number of various types of option, like labeling the peak, or if you sample have the noise, very much noise, so we can reduce the noise with the help of smoothing effect. So here some manipulation items are there, functions are there, like purity. The purity, we can check the purity of the sample. The sample will compare with the standard. The basic in pharmaceutical industry, they follow this purity formula or the purity option. They are running the standard sample on any technique like transmission or reflectant technique, using KBR palette technique or ATR technique. They are running the standard. As soon as they run the standard, same parameter or method parameter apply to the sample also, and they run the sample, and they match the data, spectrum data with sample spectrum data with the standard, and get the purity of the sample. Then they will set the criteria for the purity. If this purity criteria match with the standard, then sample will get passed. Then second option is a peak table. If you want to label the specific peak with a wave number or name, we can use the peak table. Majorly it for the labeling the wave number of multiple. If your sample having a multiple peak, but we want to specify the specific peak for this specific spectrum. So with the help of peak, uh, uh, you can label the peak for the specific spectrum. Here the right hand side, if you are selecting the peak from the manipulation table, the right hand side, we have to set the threshold and noise level for the calculating the peak level tables. After selecting the threshold and noise level, we have to just click on the calculate and select the OK. Automatically labeling of peak will be see on the screen. But majority of the peak, small peak are not get labeled due to the threshold. Due to the threshold. If you want to label the peak manually, the software has a priority, or the software has a facility to make the peak labeling manually also. Then ATR correction. ATR correction mainly used for if sample having customer having the sample which is run in the transmission method. So now customer using ATR for the analysis of sample. So by using the ATR, the sample is run with on the ATR. With the ATR correction, automatically spectrum get run with the run in the transmission mode. By using the ATR, we can correlate the spectrum of ATR and transmission ATR spectrum. It will be look like the same after the applying the ATR correction. And fourth is the smoothing. Smoothing is performed to reduce the noise of data. Majorly, we are not recommended for the do the smoothing or spectra. It means that you are manipulating your data. If you want to smoothing your data or spectrum or reduce the noise, you have to do atmospheric correction, or you can increase your resolution like 4 centimeter to 8 centimeter. It will be automatically reduce your noise, or you can increase your number of scan, so automatically noise will be reduced. So we will not recommend to use smoothing manipulation function. It is available in a software, but automatically we can manipulate that spectrum data. So if you not go for the smoothing, you can increase the number of scan, you can increase the resolution power like 4 to 8. Automatically your software give the your spectrum will be get smooth baseline. With the help of FTR, we can quantify the unknown sample. Here one window will there. After clicking on lab solution software, we are going to in quantitation tab. In quantitation tab, the sample standard or sample, the standard and sample we have to run in spectrum mode. First you have to run the standard and sample in spectrum mode, save the spectrum and spectrum data for standard and sample. After save the both the spectra for sample and standard, we have to go in lab solution IR software, then go to the quantitation tab. In quantitation tab, there are two windows we are seeing over here. For upper window is for the standard and lower is window for the sample. We have to just import that spectrum, standard spectrum in standard tab, and sample spectrum in sample spectrum in sample tab. For here we have to prepare one method for the quantitation. We have to select one major peak or marker peak, which is get increased by increasing the concentration of the standard. So we have to in whole spectrum we have to select one marker peak which concentration get increased by increasing the concentration. So select that peak in calibration curve. For the calibration curve, automatically we can get the calibration curve. Then unknown sample we can run that calibration curve. We get the unknown concentration for the unknown sample, concentration for the unknown sample by using. But FTR is a qualitative, majorly used for qualitative analysis, not quantitative. So for UV is a majorly used for quantitative analysis. So most of the customer, they are not using FTR for the quantitative, but few pharma customer, they are using FTR for the quantitation analysis, because it is a very easy technique. You have to run sample in the ATR. It will take within a 1 or 2 minutes for the getting the one sample analysis data. So very few customers, they are using the quantitation method. So otherwise most of the customer getting get analysis on qualitative analysis on FTR only. Okay. This is accessories which are used for the analysis in FTR. With the help of accessory, we can analyze multiple sample like various sample like liquid, solid, gas sample. There are two types of techniques we can use for the sample analysis: transmission technique or the reflection technique. With the help of transmission technique, we can analyze solid sample, liquid sample, gas sample. For the solid sample, we can use transmission technique like a KBR palette technique or KBR palette technique. In KBR palette technique, we have to mix our sample with the KBR with some quantity like 2 mg or 1:100 proportion. Like 2 mg of sample we have to take and 200 mg of KBR sample we have to take and grind with the fine powder. Then we are placed into the pallet making device like mini hand press, and they apply the pressure around 1 to 2 ton, 1 to 2 ton for the mini hand press, or we can apply the hydraulic pressure also which go up to the 8 ton. Then it will be make the die and take the transmittance of the sample. For the background analysis, we have to take a background for in KBR palette. We have to prepare blank KBR palette for the background correction and sample plus KBR for the sample analysis. Then, but the transmission technique is very good technique because we are directly penetrate our sample. Sample is passing through the this KBR palette and reach to the detector. So response of this transmission technique or KBR palette technique is much more higher than ATR technique. ATR is a only reflective technique. So energy may get reduced by when using of ATR, but in transmission technique energy is very high. So most of the pharma they are now using ATR, but previously they are more preferably using the transmission technique with the help of KBR palette because the energy is very high. No matter the peaks will be not change, but energy will differ. So as my knowledge, transmission technique having the more energy and more response to the spectrum as compared with the ATR technique. So as sir has already explained the various accessories they are using for liquid like demountable cell, thick thickness cell, gas cell also.
Amol, I think you have to stop in 1 or 2 minutes, Amol.
Yes sir, yes sir. I have already completed because you are already completed all this. Yes. So we can use the solid sample, liquid sample and gas sample also. With the help of this demountable cell, thickness cell for the liquid, quad cell for the gas analysis. With the ATR we can analyze liquid or gas sample also, and DRS we can analyze solid powder sample also. So this technique already sir has explained, so I'm not going into the detail. Okay, thank you sir.
Thank you, Amol.
Thank you.
So now, sir, a few questions.
Yeah, please.
There are actually 11 questions. We will see whether we can take all or not. One Birindra, for a cerium oxide, CO bond peak would be observed at what position in FTIR spectra?
Which sample?
Cerium oxide, sir.
Cerium oxide basically it comes under an inorganic analysis of FTIR. I do not know exact wave number position, but it will be definitely less than 400. Less than 400.
Yes, the bending vibrations only we should
it will be less than 400.
Yes.
It is possible. There is a whole chapter on inorganic analysis by FTR. Most of the meaningful vibrational the peaks we can see most of the time below 400.
Yes. And Prabha, Sir, if a laser source of monochromatic light is failed, is it possible to replace it in the affordable cost? Or it can be replaced by the research scholar or any IR analyst to come and replace?
First of all, if your laser light is failed, the service engineer has to come and replace it. You cannot do anything about it. The service engineer has to come and open up the equipment and replace it. And the cost part, I'm not very sure, but it will be a costly part, but I do not know exactly what will be the cost. That you'll have to ask the salesperson. But all probability, it will be a costly part, but I do not know how much. But it is to be replaced by the service person only.
Okay.
You cannot replace it.
So Siddheshwaran asking, what is the role of laser in IR spectrophotometer?
I mean, this was actually explained. The IR laser beam is used as a internal reference light for the measurement of very precise measurement of the detector signal as well as the moving mirror velocity. So this is to be very precisely measured, and that can be done only with the help of a laser. So the main advantage, the main reason why we are having a laser light inside is for the precise measurement of detector signal, that is called the sampling rate, as well as the measurement of the moving mirror velocity.
Okay, another question from Shinde. Why in UV spectrograph representing?
What I understand the question is the UV we are using wavelength, and here we are using wave number.
Wave number,
very
yes.
Simple. It's very simple. You can use both actually, there is no issue. But when you talk about wavelength and wave number, they are interconvertible. So if you want to talk in terms of wavelength, in IR also we can do that. There in place, in that case, instead of talking in terms of wave number, we talk in terms of micrometer wavelength. I can do that. So, but only thing we are using inverse centimeter because that is more convenient for us. But otherwise, we can talk in terms of wavelength also in IR. I will talk in terms of micrometer. So that's why I told you wavelength can be, the wavelength range in IR can be expressed as 0.8 micrometer to 1000 micrometer. And when I am converting it to wavelength, wave number, it is from 12,500 inverse centimeter to 10 inverse centimeter. So either you can use wavelength or wave number, but wave number is more convenient. That's all. Both are correct.
And another question is, in FTR case, identifying overlapping bands for derivative analysis is using, which range is helpful for conforming the inorganic structure? His question is, is there any provision like yesterday UV visible spectroscopy, can we determine derivative spectra for IR spectrum also? Like yesterday.
Normally we don't. In the case of IR.
Okay.
Why we get a overlapping? If there is an overlapping case, normally what we do, we can go for, there is an option, as Amol has told, there is an option for adjusting the resolution. Normally we have 4 resolution. We have got a complete range, say from 0.9 resolution up to 16 resolution. If you feel there is an overlapping, the moment you reduce the resolution, your resolution will improve and an overlapping peak can be separated.
Another question, Siddheshwaran asking, which ATR method is qualitatively more accurate for a crystal sample? Vertical or horizontal?
I will always recommend horizontal. Because vertical is not very popular, and it is normally used for, I told you the type of samples that can be analyzed by vertical ATR. Only film samples or some cable samples or packaging material only can be analyzed. So horizontal is more vertical, more versatile, more popular, more comfortable, more useful.
And another question is, why does the sample needs 810 pressure in hydraulic and 210 in hand press?
Hand press? Yeah. Amol, can you tell this?
Yes, sir. Okay. For hand press having the pressure around 2 ton, no issue. But there are diameter we are using a hand press pressure, and the diameter is around 7 mm. And when we are using hydraulic press, the diameter will be around 13 to 13 mm. The thickness will be very high. So we are using more sample for the hydraulic press. So when we are applying the pressure 2 ton, so the die will not get perfect. So we have to apply more pressure to get uniform die. So it doesn't mean that 2 ton pressure give the low resolution or low energy, or 8 ton give the high resolution, or it doesn't mean. It will be give same spectrum for the both low 2 ton or 8 ton. No issue with that. Sir, if you want to add someone.
No, it's okay.
No. Another question is there any database available for identification of microplastics using FTIR?
We have got polymer database available.
Yes.
But these are all optional items. You have to buy separately. It will not come by itself.
Sir, can I add some?
Yeah, please.
There are different library which are different industry spectrum they are adding in lab solution software. For the polymeric system, Shimadzu have the different library. We have to purchase that library and get installed into lab solution IR. So automatically you can get correlate your spectrum, any sample, polymeric sample with this library. So automatically you can get the library mass spectrum, and we can get the how much your sample spectrum get matched with the specific sample spectrum. We get idea the what is the present in your sample from the library. So but it is optional. You have to buy. You have to buy that.
Okay, another question is Siddheshwaran asking, both IR and laser has same velocity. Please explain, is it carrier waves?
What is that? I didn't get the question.
Both IR and laser has same velocity. Please explain, is it carrier waves?
Carrier waves means what? Basically, what is meant by carrier waves?
See, this
both are having same optical path.
Yes.
They are passing to the sample. They are passing to the interferometer. Have the same optical path. The only difference is the moment it comes out of the interferometer, laser is taken out and separately detected by a laser detector. We have a separate laser detector inside. Only the IR light will be passing through the sample compartment. The laser light is not passing through the sample compartment. But they are having the same optical path. They are moving together till the interferometer. That's all. They are coming from two different sources. Laser is coming from the laser gun. IR is coming from your IR source. But they are passing, having the same optical path length, optical path. And once it comes out, the laser is taken separately and IR light will pass through sample.
The one last question, sir. Which is best for microplastics identification? ATR, FTR, or FTRI?
Sorry, FT?
Which is best for microplastics identification? ATR, FTIR, or FTRI? What is this FTRI?
What is this FTRI?
FTRI, I don't know. Maybe ATR or FTIR.
You can use an ATR for this, no issue. You can use an ATR along with an FTIR, but I have not heard of what is FTRI.
FTIR.
Must be FTIR, but you can use ATR. You can use
it. Chat box. Okay.
You can use an ATR.
Sir, in some one more question in the chat box.
Yeah, please.
In the FTIR instrument, how to place the sample without film sample holder?
Without film sample holder. If it is a film sample, is he talking about a film sample?
It seems.
Film sample, either if you have got a film holder, you can keep it. Otherwise, you can keep the film on the ATR crystal itself as it is. No issue. If you have got an HATR, you can keep the film on the crystal and record the spectrum.
How to?
Or even you can use the film, even you can keep it on a diamond ATR also, and then you can get the spectrum, no issue.
And one more question, how to identify the pellet pressure?
Pellet pressure?
Pellet pressure, what is
meant by pellet pressure? I don't know.
I don't know. This is maybe...
Pellet pressure means, is he referring to the pressure that is applied for making
yes,
potassium bromide? You can read the pressure on the gauge. There is a readout gauge, you can read the pressure on the gauge.
Yes.
Pressure we can see on the gauge when we are preparing the pellet. Now that time we can easily see the pressure. What pressure we applied and what pressure we are getting.
Yeah, correct.
So that can be very visible.
Yeah. What Madha said is correct.
Okay. Sir, that's it for now. All the questions are answered. So we can close the session. Thank you very much, sir. That was very exclusive session today on all types of FTIR accessories. We have learned a lot. So participants, thanks for your active participation today, and sir has displayed some questions at the end of the session before demo. Please try to work at home and come back tomorrow with your answers. And before starting tomorrow's session, sir is going to answer those questions, and we will start session by 9:45 itself.
My only request to the participants, be on time so that we can start on time, we can end on time.
Yes, that's the thing.
Because today also we had to wait for the people to come. So please be here by at least by 9:50 so that sharp 10 o'clock we can start.
Yeah, tomorrow's session will be on thermoanalytical techniques, which is very interesting and important technique in pharmaceutical field. So see you all tomorrow, same time by 9:45 a.m.
Yeah, correct.
So that we can so that we can finish the session exactly at 1 p.m.
1 o'clock. Yes.
Thank you, sir. With this, I will